All right. Theoretically, we are now live, and hopefully, it's going to the place it's supposed to go. I don't know. I haven't done it that many times. But so what we're doing today is just going to have a little conversation. I tentatively named this "Layman's Lines" as a little. I don't know, just kind of a hats off to fun topics and stuff. So today, what we're doing is I met Jerry online, and basically he's just a dude who's interested in the ether and topics like that. And he had a lot of questions. I'm like, man, uh, I would like to answer the questions that just general people have, because it's like, that's the best way to do things. And he's a little skeptical about the ether. That's perfect for me. It's exactly what I'm looking for, is people who are kind of interested in the whole thing, the whole physics thing, and what's reality, what the heck's going on, and just have a little conversation. So that's what we're doing today, is just a layman's conversation. Talk about the ether is real. What? So I'm gonna hit my little intro here, see if we can get that to work out properly, and then we'll be right back. All right, man. So let's see. Now we've talked about things. We've gone a little bit through some different things we've talked about the ether, and let's see. Apparently you were on the old anti-relativity site, like way back in the day, right? Like you were. Yeah. So okay. So I've got this site, and people are going to take it the wrong way, because I actually do believe in relativity. Anti-relativity is something that is a not the antithesis of it, but simply a inverted version of it. In other words, the whole idea is that there is an inverted version of relativity alongside regular relativity. I'm going to hit sometimes there's an echo problem, so I'm going to mute you for a second and unmute you to see if it fixes it. Generally, it does that every time. I'm gonna mute myself and see if that works.
All right.
What's weird with this program is it sometimes it fouls up a little bit every once in a while whenever you play a video. So I got to talk to him about that. But so yeah, I don't know if there's anybody watching yet or anything like that, but this is being recorded. So when people catch up, we'll be able to talk about a few things. But we're just kind of doing like a hanging out in a bar or a library or wherever, sort of conversation. And before we get started with some of the questions that Jerry has compiled, that he wants to be like, what is this? What about these problems or what have you? The first thing I wanted to cover with you, Jerry, is the idea of a wave. So like because that's going to be the most critical thing, because you ask me frequently, what is the why would there be ether, why is that even necessary? And you've been like, yeah, hey, I agree with Einstein that the ether is not necessary. Well, first I'm gonna stop you right there on that. Einstein was only saying he didn't think it was necessary for the calculations, but by 1920 he said space without ether is unthinkable. Okay, that he had a whole speech in 1920, which is 15 years after special relativity and 5 years after general relativity, where he laid out that it's not just necessary. Having space without it is absolutely unthinkable. You have to have some sort of substrate for all the things for general relativity to even work out. So that's something a lot of people are going to have the exact same misconception you do, that Einstein eliminated the ether, when in fact he did not. He very strongly believed in ether. And then what people are going to say there is like, oh, well, he's just talking about gravitational fields, and that being the ether. To an extent, that there's some truth to that viewpoint, but that's actually somewhat inaccurate as well. It's an oversimplification of what it was that he was talking about. He was talking about specifically gravity. He was talking about Ernst Mach's idea of the way in which the mean gravitational influences of the entire universe make up a preferred frame. And there's a lot of things having to do with constancy and stuff like that, but we'll put all that to the
real quick. What is a preferred frame? Is that like
In other words, that there's one frame that is more special or more. That's not a good word for it because of one of the quotes, but it is more. A universal frame of reference is basically whenever you're talking about relativity, most people will teach you that there is no one frame that is more right or true or correct than all the rest. That is actually not true of general relativity at all in the slightest. What they're doing is teaching you a deprecated theory. In other words, special relativity is deprecated in favor of its upgrade, general relativity. And in general relativity, there is definitely a preferred universal frame, and that came initially from Ernst Mach's suggestions that when a train stops and you're thrown forward, it's the stars that throw you forward. In other words, it's the idea is the gravitational mean of the universe makes up a preferred frame, and that is the reason why acceleration works in the way in which it does. And this is something Einstein wholeheartedly agreed with, and that's what he was referring to when he said space without ether is unthinkable. So there is this point where, after Einstein had plenty of time to think about his theories, that the initial statement that was true, that you didn't necessarily have to consider, just like, okay, so there's something called electron holes that we use today in like electrical engineering. It's completely, everybody who knows about electron holes, if you know about them, they're also not real. They don't exist. They're just a handy method of notation. It's useful as a teaching and thinking tool, but it's not real. And so that understanding that there are these concepts in science that we use as handy tools and things like that is very important to this specific conversation. So there are some confusions that I'll try to clear up for you there. But the first thing I want to start with, though, is the idea of a wave. That's really, really important. So you understand that I need to kind of to cover this one particular point before we go any further, and that is, you understand that if I take all the water out of the ocean, there's no waves in the ocean, right? That's easy. So why is that? And what exactly makes a wave a wave? What is a wave? And can waves be something other than the changes to a medium? And I'm going to tell you that the answer is no, and that a wave is an action. So like you can go for a jog and you can call it a thing, but if you remove the jogger, there is no jog. A jog doesn't exist on its own. It's a property. It is an action. It is something that a jogger does. So I went for a jog doesn't mean that I could hold a jog in my hand. It means that there's just an action. A wave is a verb. It is not a noun. And that is why when you look out in the ocean, you think of waves and you think they exist, but they don't. They're a perception that you have about actions. And you can cut them up because there's an up and a down. And so because there's an up and a down on those ocean waves, you think of them as things, but they're not things, they're actions. And so that's one of the most important things to understand. So then somebody else might say, well, hey, I can talk about these, I can see a wave in data. It goes up and down and up and down. Yes, but here's the thing. A wave is a mechanical action that can have mechanical impact on other waves. This is crucial. This is critically important to understand that a wave is either a compression and rarefaction, or it is a twist or some sort of displacement from equilibrium. And because it is a mechanical change in some sort of stresses or something of that nature, where there's some sort of change in the equilibrium of a substance, that once you displace it from that equilibrium, it tries to return to the equilibrium by some sort of restorative force. So in other words, like something pulling molecules back together, or in a crowds have waves. You step into a crowd, and if they're a very a fastidious group, and they don't like this, let's say we took a crowd of people who really are don't like to be touched, and they try to maintain as much room between each other as possible. The moment you step into that crowd, a wave will actually propagate, because people will try to move away from you, and then in their movement away from you to try to middle it, the person next to them will also have to move. And so that'll spread out as a wave. We see waves in traffic. We see all these different types of waves in various mediums. And then when people think of a wave as, oh, it's just the up and down of the data, the problem there is there can't be a mechanical interaction. There cannot be a way in which one wave can interfere with another. That's the primary property of waves, is that they can interfere. And that is, if I've got a compression, when it reaches a rarefaction and those two interact, they can cancel out. So in other words, when a peak and a trough of a wave interact, there's a canceling out that can occur. And that's why we can see these different things that happen with waves, is because of the way in which they act. And so understanding that this means that having there's been 100 years of people teaching you a wave can exist without a medium, and that's magical thinking. And that is the primary single starting place for all of this conversation about ether, is the fact that any concept of a wave without a medium is entirely a magical concept. So I just want to start with that, and then we can go from there.
All right. I have a question.
All right.
Is the wave is the ether itself a wave, or does it propagate the waves?
It propagates the waves. So everything in the universe is made of the ether, and matter is just one of the various behaviors of that substance, is the idea in ether theory. Now the ether theory that I'm referring to here actually descends all the way from 200 years ago and up through. There's a specific line that goes right into relativity. In other words, a line of ether theory that underpins relativity. That relativity didn't spring magically into Einstein's head. It came from 150 years of ether theory, and was specifically Lorentz's transform was specifically and only about ether. Fitzgerald, who first suggested the Lorentz transform, the first basic idea of the Lorentz transform, which gave us relativity, it was entirely based on the way that light, the wave in the ether, acts. So let's try to get to some of your different questions that you have. And let me also check to see if there are any comments, just in case somebody's here. Okay, no comments yet.
All right. Well, I have there in the box there. Does the ether physically exist?
Okay. Space? Here's the thing: the issue of physicality is a difficult question, because whenever you get into what we think of physical, in this concept of the ether, you have to sort of turn your view of the universe inside out. And so this is, like I said, this is not particularly new. This is just simply putting all of it together in a way that is from the perspective of modern times and modern experimentation. And that is that the ether is the real thing. In other words, that matter is the thing that is actually the more ephemeral and more just sort of a side effect, an epiphenomenon is what it's called, of the ether's action. So when you talk about physically real, it is super physical. In other words, it is greater than physically real, because what we think of as physically real is matter. But when you think about like a vortex in water, you can look at like you stir your cup, you got a cup of water, you can see the vortex inside of there. You think of it as a physically extant thing. It is, you think of it as physically real, but when you think about it long enough, you recognize, oh wait, it's just what the water's doing, and there's a borderline I can see, and that's what that little vortex in the center is the borderlines on the ether, or on the water in this case. But the same thing is also true of the ether when you use Kelvin's not vortex concept of the atom. So yes, the ether is physically real in that it is super physical, it is more physical, and it is what, whenever we think of as empty space, that is simply ether not behaving like it does with matter. What's happening with matter is that the ether is spinning so rapidly that it's crossing a transitional point, just like a tornado. A tornado, you can't see a tornado initially when it first starts, because it's invisible in the air, until it goes, it's spinning so fast that it changes the relative humidity to the point at which water molecules start to form into droplets, and then you start to see the fog form. That's where the fog is forming, is because it's crossed a threshold because of the changes in the air pressure, because of the rotation of the air. And so you see the borderlines, but you couldn't see it beforehand. even though it was still there, there was still air spinning. And so the tornado existed before you could see the funnel cloud. And so that's part of what you need to understand about what we think of as space versus matter. Matter is just when space is doing something so rapidly, it crosses a threshold, and we then perceive it in a way different than we normally do.
Well, the way that atoms are real, the way that the ocean waves work, that's all. That's physical in a different way. If ether is physical, it's physical in a very different way.
Yeah, you could say that. In other words, the behaviors of physical reality descend from this.
Yeah. Well, okay. Well, here's another question. Does the ether extend infinitely, or is it only finite? Or is it necessarily relevant to the ether itself? I mean, it's just an interesting question.
Yeah, when it comes to to ether theory, that's one of those, it's turtles all the way down. Are you familiar with that? Where it's yeah. So the idea is like, is there a bottom level? But whenever we try to put a bottom level on something, it's useful to say there's a bottom level. And I think that perhaps the ether may be particulate down near the Planck level. And actually have a model for specifically the shape of ether particles, and a reason why it possesses chirality. Because one of the things that happens is that if a substance spins in a particular direction, like right-hand rule, then every time it's perturbed, then there's a characteristic called chirality that it possesses. And so you have to have some explanation for that. And I do have an explanation for why it is that the ether behaves according to the right hand rule. But the point is that when you talk about whether or not it's infinite, that's a question that isn't terrifically important, I suppose. There's a point at which that becomes a question of infinite regress. And is the universe infinite? My personal feelings about it are that there's no such thing as beginnings or endings anyway. That concept of a beginning or an end is entirely a human made concept, and that we basically, any animal or any creature any cognitive system requires that there be a loop back. You got to be able to turn around and reuse information. There has to be, you can't just keep going. There's a point at which you have to have some way to break out of the forward motion and return to a previous point to be able to make information useful. There has to be beginnings and endings for any collection of information. You have to be able to make a decision, for instance. Like I relate this to, think about if a rabbit that was about to be eaten by a fox considered things too much, like thought too far into the future. It's like, well, if I once we've gone 12 miles that direction in our chase, and if the rabbit thinks about all those different things, it's going to be killed because there's only so much processing time that its brain has. So it has to minimize the consideration down to the most relevant possible smallest set of information. And so there's different sets of information. Those are loops, basically loop backs. And so there is the smaller loops and there are larger loops of consideration. And I think that all of that is just what's necessary for any being to survive, is that we have these beginnings and endings that we create. But I don't believe there's any such thing. In other words, I don't think that there is any real borderline between anything in the universe. And so therefore, I don't know that there's ever been a beginning. I don't think there is a beginning to the universe. I don't think there is an end to the universe in the time-wise way, nor in the space-wise way. I think that infinite is the greater reality, and that finite things are just a need for us as finite beings to conceive of reality.
Here's a question that the way that Einstein eventually accepted the ether, did he invalidate the space-time continuum, or how would you see that similar to the ether?
Okay, so the space-time continuum, why is it a continuum? That comes from Minkowski. So in 1907, Minkowski published, I don't remember the name of it because, I actually, Minkowski pisses me off because he's the main problem why things have gone wrong. And it's not really his fault as much as because he was developing on the no ether idea that kind of is there in the 1905 Einstein paper, Special Relativity. The problem is Minkowski put out a paper in 1907, then died in 1909. And Minkowski was a good friend of Hilbert and a lot of the other people in this very, very small physics community. And so when he developed space-time, what space-time is, the continuum. Why is it a continuum? Why do you have this idea of space and time seeming to be this one sort of thing? That comes from the idea of isotropic constancy. So this is something we've talked about before, whether there's anisotropic or isotropic constancy. And there's that video, which I should probably, give a link to anybody who's watching. So let's see if I can find it. But if you, let's see, I think if you just Google one-way speed of light.
Yeah, we had talked a little bit about that yesterday, I think, about the isotropic.
I just want any viewers who watch this to be able to keep up with this. Speed of light. Then you should find a video by, one of the first ones there by Veritasium. It's got this little through it. I don't know if can I put that up on the screen somehow? I might not be able to. Well, anyway, there's like a line through it, and it says impossible on it because there's this idea that we cannot possibly measure the one-way speed of light. And so this is something that has plagued us since Minkowski's paper, since 1907. And it's something that my most recent paper is about. And it's specifically the idea that it makes Minkowski space-time completely untestable if we cannot actually measure the one-way speed of light. So why is it that you would have space and time conjoined together into this one thing called space-time? And like I said, Minkowski did that. And the reason for that, where we have, if you're familiar with the relative simultaneity, let's just quickly, briefly go over that. That is where the idea that what is simultaneous for one observer is not truly simultaneous for another. So if I'm in motion with respect to you, say you're the ground-based observer, and two supernovas go off, at different places, and I'm passing by the Earth near the speed of light. You're on Earth, and you're like, you would say, yeah, those two supernovas, I saw them both. That means they both exploded at exactly the same time. But according to me, I will receive their signals at different times because they literally, from my frame of reference, which is theoretically just as valid as your frame of reference, they exploded at two different times. In other words, our simultaneity is completely different. Now that, once again, I told you before that general relativity actually has a preferred frame. So in other words, general relativity says my idea of what's simultaneous is not just as good as your idea of simultaneous. That's from special relativity, the deprecated theory from 1905. So there's 1905 Einstein, 1907 Minkowski, then 1915 Einstein again. And so understanding this timeline of events and how we have the telephone game where people are teaching the deprecated theory because general relativity is harder to understand.
Yeah,
so people are still teaching things from there. And when Einstein was first made aware of Minkowski's paper, he said, "Now that the mathematicians have gotten a hold of the theory of relativity, I don't understand it myself anymore." And that was meant as a kind of a laughing joke. But here's the thing: Einstein actually studied under Minkowski, and so Minkowski, his best friend Hilbert, and a bunch of the students all jumped Einstein's ass on a public forum. I think it was I forget what the name of the paper was, after Minkowski died, because of his lack of using Minkowski's work. In other words, they all felt that he should be honoring his mentor and using Minkowski's work on special relativity. And so because of that, Einstein was socially pressured into using Minkowski's ideas. But here's the thing. So that's all the social stuff around why we still talk about this deprecated theory. How did all that happen? Why is it still confusing us? And why is it that even though Einstein said we have to throw away constancy, there is an ether? Why when he said all those things, why are we not taught that? Is because of this social event, of all of these scientists all being friends, and Minkowski abruptly dying. Minkowski wasn't sick for a long time. He had his appendix ruptured, and like I said, Hilbert, where there's things in physics called Hilbert spaces. There's these are some of the central people, and there just weren't that many of them, and so it was a big social event. There was supposed to be this meeting between Poincaré and Minkowski that Hilbert was setting up, and they were going to talk things out, but then it ended up that Minkowski had died, and they never were able to talk about things. So there's all these different social events that led to this thing where space-time conjoinment from Minkowski's 1907 paper continued forward. Now, let me explain why that is. It is technically now, according to the most recent ideas, that we cannot we cannot test the one-way speed of light. And that's that video that, for anybody who's watching, just Google one-way speed of light, watch that Veritasium video, pause this one, go watch it, come back. The idea is that the one-way speed of light versus the two-way speed of light is because of what it was that Lorentz intended. Okay, so you have to travel back to 1887 was the Michelson-Morley experiment. What was the second Michelson-Morley experiment? It was the confirmation of an earlier experiment that was not quite as precise. But it's the one that everyone knows about. And after that, Fitzgerald, who was a scientist of the day, suggested what was called I'm gonna have to mute you here for just a second. I'm gonna mute us both because I could hear myself popping back through on your mic. It's making a weird sound. Let's do this real quick. See if did that work. Yeah, it looks like it did. If it didn't, I'm gonna mute you for just a second while I do my little spiel here. Yeah, let me just mute for a second while I do my spiel. All right, so where was I? So Minkowski, doggone it. What point was I at? Because I did
about Fitzgerald, maybe with link.
Okay, yes. All right, so he suggested the change factor. So in other words, the math for the change factor, as he suggested it, and what he suggested and why he suggested it specifically is that he believed that, well, perhaps what is happening, why do we have this Michelson-Morley null? And so the idea is with the Michelson-Morley is that you shoot light upstream in a river, because that's what the ether is like if it's moving. And that's an assumption, of course. They assumed that the ether would be moving across their experiment from east to west based upon the Earth's movement around the sun, and then also some component based upon the sun's movement through the universe. And it was actually the sun's movement through the universe that was the first thing that they wanted to test, not the Earth's movement around the sun. They already knew the speed of that based upon some interesting calculations about the moons of Jupiter and how various eclipse things were occurring there with that. So they were able to already determine our speed around the sun as around 30 kilometers per second. And so what they wanted to measure initially with Michelson-Morley experiment was the speed of the Earth, through of the solar system through our galaxy. And what they ended up finding, of course, was that there's this assumption. You go, all right, well, if the ether, if we're moving through the ether, and the ether is stationary, let's say with the galactic center, there's some sort of assumption, huge, gargantuan assumption there, then we should be able to measure an effect of going upstream and downstream. So it's like a swimmer. Like if you put a swimmer in a river and you put two markers, he could be swimming in the water at 20 miles an hour. But if the river is going 10 miles an hour, then his speed that you're going to mark along the bank is not going to be the 20 miles an hour in the water. You're going to see him going 10 miles an hour upstream and then 10 plus 20 downstream, right? Did I say that right? Sometimes I have to write this. Write the ones I'm talking about down. But let's unmute you here for a second. But that makes sense, right? It's going to add. It's going to take. If you're going 20 miles an hour and you got a 10-mile-an-hour river, then you're going to get you're going to be going 10 miles an hour
up the river
the ground. Do what? And
the
then
flow of the river will push you.
Right, and then 30 miles an hour going that way downstream. So it's going to cut you in half, and then it's going to and then it's going to add back a the did I say 10? Yes. Okay. So yeah, it's going to be 30 going back downstream. So much better writing it down than saying it out loud. Saying numbers out loud without writing it down, it's just always a bad idea. But anyway, so the point is that you have this upstream and downstream effect, and being able to measure that with light, because the idea is that if you drop a pebble in a river, for instance, as the river's going by, you drop it. If it's a very placid river, you'll see the rings go out, but those rings will be moving with the river, right? Because it's in the water. The waves travel in their medium. If the whole medium is moving by, then there's going to be another component to that motion that you have to think about. And so that's the whole idea that they've got here, is they think that waves in the ether, called light, are going to be carried by the ether. So therefore, if they shoot light up and down and race it with light going back and forth, then they should be able to determine how fast the river is moving. And that's the idea. Yep.
Yeah. Oh, dealing with the one way travel of the isotropic principle constancy, because I've taken that to mean that the light may travel like full speed ahead, and then when it returns, like from the reflection, that because it reflects, it would go slower. That was my impression. However, the meaning of that is because of the river effect, because of the
well, it's specifically isotropic versus anisotropic constancy. I'm going to try to explain to you here in just a second. So the idea here is that if it goes up and back, then there's going to be, a certain amount of change to the whole round trip, right? So like if I go 20 miles an hour upstream normally, but that's a 10-mile-an-hour river, so it's going to be cutting me down to 10 miles an hour. And then if I've got 10 miles between my markers on this river, then it's going to, it's going to be one speed in one direction that I'm going to complete the whole route. And it's going to be a different amount that I complete the route on the way back. Now, and there's a calculation for that I'll try to avoid, because like I said, without writing things down, it's a very bad idea. But
why wouldn't that seem around about the same? Like the trip to one side and the trip to the other, why wouldn't they be roughly the same amount of time?
Okay, so you're having that one intuition. This is actually an intuition. I'm glad you brought that up. So what you're saying is, like, if there's a river traveling along and if it's cutting down your time going up, and then it's adding to your speed going back down, then shouldn't it cancel out? That's kind of an intuition that some people might have. And of course, the answer is no, because of that thing. So I wish I had I should have done this. Next time I do this, I'm going to have a little thing to write on. I'm going to make sure that I can write stuff down that we can read. So I'm glad you're helping me out with this. I'm going to do that next time. So here's the thing. If you're going upstream against it, and your speed is always 20, that's your ability to swim is 20, period. You always swim at that speed. And if you're going upstream, then according to the markers along the bank, you on a 10-mile-an-hour river, you're only going 10 miles an hour upstream, because it's subtracting 10, right? Yeah. But then if your speed is 20 and you turn around the other direction, what's your speed now going downstream? It's 30.
Oh yeah. I see what you're saying now. I had in mind of going across the river, like literally going across while being pushed, and that when you return, that there'll be roughly the same amount that being pushed down the river.
And here's the thing: that is the cross river and back is the most fascinating part, because you have to swim to be able to go directly across. You have to swim at an angle upstream.
Yeah.
In other words, whenever you're going to go, you have to swim at an angle upstream the whole time. You're swimming at an angle. And to take a path that goes straight across and back, right?
Yeah.
And here's the thing: that amount is exactly the change factor. In other words, like if you you have to measure it based upon, there's a combination of your speed as a swimmer versus the speed of the river. And whenever you use any calculator, you can go to relativitycalculator.com, and what you'll find is if your speed, like if your speed is half the speed, in other words, like if this, here's the thing, you have to understand that the swimmer is light in this instance, and so the speeds that you're comparing are the speed of the river versus the speed of the light traveling through it. So if the speed of the river is basically what we're talking about here is 0.5 c, so half of the speed of the swimmer travels 20, river travels 10, then you'll find that in a relativity calculator it's 0.866 or 1.1547. I actually use that calculation frequently, so I remember it. And those are the two versions. And that's actually the distance that you end up traveling. In other words, if you normally travel 10 across up, to go up at that angle, the actual distance you will travel to go up there as the river is, because you're having to go at an angle, the amount of water that you will traverse ends up being 11 point something, whatever I just said, times 10, 1.1547. So that's the point, is that's what the calculation from Lorentz is dealing with light as a swimmer in a river. But here's the thing. If you have this swimmer going upstream and downstream, that's a specific number, and it's actually different from the swimmer going upstream and downstream, because the distance, if you don't change those markers, the distance you'll travel in the water at that 2-to-1 ratio that I gave you of a swimmer going 20 and the distance being 10, or the speed of the river being 10, I mean, then what you'll actually travel is 1.333. And what you'll find is that the Lorentz factor squared, it gives you that normal amount. So you actually have to find the square root of what your normal extra distance would be. So in other words, so normally you'd end up traveling 1.333 up and back down in a river, and this but going across and back, it'd be 1.1547. So the difference between those two, that is why why Fitzgerald suggested things must shorten up to make those two paths across and back and up and down be the same on average.
Would you say that physically occurs though? The way that, like with length contraction of
right. Okay, but we have to do this step by step. So in other words, so you're actually jumping ahead to the fact that I've said that length contraction does physically occur, that it's a real effect that does occur, just like relativity says it does, and I agree with that. Yes, I do agree with that. But let's take it one step at a time, because there's a lot of different things that you have to understand in a kind of a mechanical basis. So we're starting from the idea that there's this that light is a mechanical wave in a medium. That is not part of what you're taught about relativity today. You're taught it's this special magical thing that it behaves in a completely different manner than all other waves in the universe. And a lot of people don't understand that the way we understand it, because of Minkowski space-time, is that light behaves in a way that no other wave in the entire universe does. And that is something that people don't understand what constancy means. They don't know what it means. When you hear the word constancy, you think, oh, well, it just means that light always travels the same speed. No, it doesn't. It means that it's always the same speed no matter how fast you are going, which is an entirely different thing. So let's continue to build here for just a second. So let me explain constancy for a moment and what it is what and why Minkowski confused things. Okay. So the idea of constancy. So in other words, light always travels the same speed. We'll go back for a moment and just say that if I go ahead and shorten up the markers, in other words, instead of it being 10 miles, I make it 8.66 miles that you have to travel. And then I make sure that the river is also 10 miles. Yeah, I need to. Yeah, okay. I'm getting a signal that I should mute you so that other people don't have to hear the weird feedback. So if there is a if the river is 10 miles wide and I shorten up the markers that I had 10 miles going downstream for my swimmer to 8.66, what'll end up happening is you'll travel that 11 up, 11 point, let's say 1.15, 11.5 miles up and 11.5 miles down. And it'll look like you took a path straight across and straight back of that 10-mile wide river. And then because I've set the markers to be 8.66 miles instead of the normal 10, because I've created a trick where you'll travel on average a total of 22, which is the 2 times 11, the 2 times 11.5. So it'll be 20. I guess it's actually 23.094. I actually happen to remember it. So it'll be 23.094 total round trip up and back, and 23.094 total upstream and back. But you see, it's a trick. I've just simply made them like this two swimmers that can travel exactly the same speed. They can swim exactly the same speed. Will seem like they've traveled and returned at exactly the same moment. But it's only because I was shortening up one side more than the other. This is the illusion that Fitzgerald thought was happening, and that Lorentz then specifically mathematically modeled. So the Lorentz transform, the Lorentz factor, all of these things are specifically this swimmer in a river illusion. And that is but it's an illusion that requires that you go up and back. And you see why, right? Because if I only travel the 8.66 miles up, I'll arrive at a time that doesn't really match that, because it's 11 up and back. But the 8.66, because of the fact that I've got faster speed up and faster speed down, is different than that one constantly traveling sort of upstream the entire time. There's a constant amount. And so matching them up means that going upstream and downstream is very different than back and forth. And so there theoretically is really a difference, even though the time up and back, across versus up and back are different. The same. Oh God, I'm totally messing up here. Sorry.
Oh, that's cool. Would you say that the velocity of light, in fact, does vary from whatever position you're in, or how fast you're going? That it isn't always 186,282 miles per second. Is it ever like way different, or is it always?
Absolutely. Einstein said it as well. I've got a quote. You know what? I'll find the quote real quick. Here you go. Hold on, because there are about 5 different quotes from Einstein where he said that the constancy of light must be abandoned, and he specifically said that in a gravitational field. Well, instead of misquoting him, let me just find the exact quote. I do have it written down here somewhere. Constancy of light is to be abandoned. There we go. The empirical fact of fall. I'm trying to find a short version. There's longer versions. Here we go. Second, this consequence shows that the law of the constancy of the speed of light no longer holds according to the general theory of relativity. In spaces that have gravitational fields, as a simple geometric consideration shows, the curvature of light rays only occurs in spaces where the speed of light is spatially variable. And like I said, there's a few other quotes. Let me read one of the longer ones. These are all.
Why wasn't this ever announced or put into books? Because this is my first time ever hearing this. That Einstein said that.
Because of the confusion that has to do with Minkowski, and what happens is the sociological phenomenon of orthodoxy. It happens over and over all throughout science. It's if you look into let's see, who was it? Niels Bohr, or I forget who it was that said science progresses one funeral at a time, and he was a well-known physicist. Because the truth of the matter is, there are ideas of how things work that they can't seem to go backwards, because you should have forward progress. You have to keep trying to make forward progress. And if you keep just going backwards, you get stuck. Yeah, you get stuck in a infinite regress. And so there's a point at which you have to just put a stake in the ground and develop forward. But that always creates orthodoxy, because orthodoxy is a necessity of the forward momentum required to really explore something properly. And so people don't understand that orthodoxy is it's a necessity, and so is revolution. Revolution is also a necessity, and so that's part of Kuhn's sociology of scientific revolution. So let me look at this. Actually, I think I've got a question here, and I've got everything so small I can't read it very well. Plus these glasses, well, they look steampunky. They're kind of hard to see things with. Let's see the question here. Just you see what I mean. Length contraction is not real. Okay, so the one of our viewers here saying the length contraction is not real. I was surprised when I first realized that. Check the space-time diagram, you'll see what I mean. I actually have some Minkowski diagrams that I will show that'll actually be part of the book. And why a lot of this is not in the book is because I haven't finished my book yet. That's why it's not in a book. It will be in a book. It's in the. It's. I have actually put, like on my thousands of core articles, I've been putting this this information out freely, and so it's the only reason is because, well, also the Einstein Papers project. A lot of the quotes that I'm giving you, those are from the Einstein's Papers project. I mean, that's only been around for like a decade or something. I don't know. It hasn't been around that long that they've been able to put all of his work. Excuse me, all of his notes online, all of his correspondence with various people. And so what you have is in the era before the information age, you just had the inability to really communicate certain things. And so what spreads faster is rumor, and misunderstandings are part of, the whole rumor mill. And just, it was already a difficult to understand concept. And so these subtleties that are basically, so I'm not saying relativity is false. Relativity is true. It's just understanding a specific interpretation of relativity that is Einstein's interpretation of relativity. Understanding his actual interpretation is what I'm talking about here, and it is a ether-based interpretation. The only problem is he does make one specific claim about the idea of ether, which he conceived of at the time as being entirely mediated by the gravitational potential and the interaction of these things. So kind of a field-based sort of idea of ether was that he said that, we can't think of the ether as one part moving against another. However, one of the things that is known as I need to meet you again. What's called the Lens-Thirring effect, or the frame dragging effect, is that it is well known that space actually swirls like a fluid around things like black holes and all of these things. That is an accepted part of just consensus relativity based science, that there is this effect where space is swirling around objects. So one part of space actually moves against another part of space. So that's the only thing he said wrong in his whole speech on the ether, is that one thing, that space doesn't move against itself, when according to his own theory, later on we've discovered his theory specifically predicts, and it has been proven, that space does move against itself.
Really?
Yes, absolutely. Lens-Thirring effect. You can Google it.
So ether exists within space, though.
Okay, so space itself is ether. Okay, that's the thing. It's
Really?
like that's what space is ether. In other words,
isn't there a fundamental emptiness that the ether exists on top of, or fills, or occupies?
That's the thing. I don't know that there actually is. This is the one issue I have, is that, okay, first off, I'm not sure if black hole horizons actually have a very finite border, but the idea of a black hole also goes with the idea of particles. So the only thing that I've personally really added to ether theory, because there's so much of it already done. I mean, it was done by I'm using tremendous amounts of the work of my betters, and simply adding a couple little connective things between all of these well-established aspects of basically modernized ether theory, which is relativistic. And the one thing that I add is what I call like the cavitation particle. And so like, for instance, whenever you see, are you familiar with the concept of cavitation?
No.
Okay. So can you, let's see, can you turn your echo cancellation off and then right back on again for me?
Right.
And let's try that. And I'm All right, let's see if that may
Hello?
have. All right, no, it's
Hello?
still. All right, well, we'll just have to. That's the thing. Well, you're a normal guy with normal equipment, and that's just going to be a problem that we have to deal with. So okay, what we're talking about. You can tell it's starting to get. There's too many topics. Too many topics. What were we saying?
There's a lot.
Do you remember what we were just saying before I got sidetracked by that?
About let me think. Space. If there is space and the ether exists on top, and that they've been piecing together,
okay.
or
talking about
past ideas about ether.
I wanted to tell you about cavitation. So so cavitation is what happens when a substance is basically ripped apart. So you can look at one of my favorite topics is called sonoluminescence. And if you were to Google that right now, what you'd find is that that what looks like bubbles, you'll see pictures of what looks like bubbles, and then you'll see like a light in the center of the bubble. And usually what's happening there is they're stopping it's stop motion photography, because what's happening is there's a cavity ripping open in a liquid like just water, and then slamming back together over and over. And as it slams back together and pops back out, it's actually giving off light. And so there's some argument that perhaps actually fusion is occurring, and that's why it gives off light. But anytime that there is enough shock where the ability for a substance to transfer energy from one part of it to another overcomes its elasticity, so it gets greater than its elasticity, the substance will actually rip apart, and there'll be a vacuum in between. So when you're looking at sonoluminescence or cavitation, what's actually occurring is a vacuum is ripping open in a liquid, and it looks like a bubble. It's not a bubble. A bubble has air inside it pushing the edges out, creating this spherical surface. What's happening instead is that the substance is so disturbed that the elasticity is screwed up. So an explosion comes in, and then it turns itself inside out, and the substance is just ripped apart. And then what you've got is basically kind of an anti-bubble. It's the opposite of a bubble, and that's called a cavitation. And so we have to worry about cavitation with things like rotors, like that are on ships, that the propellers. If you don't design them properly, what will happen is it'll rip the substance apart, and then when it slams back down against the edge of the propeller, it'll actually destroy some of the steel. So the water will actually create all these pock marks and holes in it. And let me give you one other example of cavitation that's really neat. And that is, just as a jet is reaching the edge of the speed of sound, you'll see these cones of white that'll pop in and out of existence. So just go, and there'll be a cone of white around it. What's happening is they're perfectly reaching the edge of the speed of sound, so that what's happening is that over and over they're resonating the air. So the sound that the jet is making, the vibrations in the air that it's making, are trying to escape, but they can't escape because the jet is going at the speed of sound. So just as it reaches the speed of sound, it's hitting the air over and over and over and pumping it full of energy, where it's ripping apart and slamming back together. And what you're seeing, that white, is tons of little cavitations in the air itself. And the reason why it's white is because the light traveling through air, it can travel in a straight line, but as it hits those cavitations, it's causing it to be warped and twisted and basically diffused. So it's a diffusion. Normally, whenever you're looking at like water droplets, it's one kind of diffusion. So like clouds and things like that look cloudy. So it looks like these things are clouds popping out around it. They're not clouds. It's not water vapor doing that. It's cavitations. The air itself is being ripped apart along a line where the sound is being is stressing air too much.
How is that something that you can see?
That's what I was explaining. Is that okay? So do you know the difference between a piece of white paper, and a mirror? The difference is that with a mirror, the light comes in and bounces off at the angle at which it comes in is the angle at which it leaves. So if it comes in at this angle, then it goes out at that angle. It comes in at this angle, then it goes right back out at that angle. So, but the thing is, with a piece of paper, the angle that it comes in is not the angle that it leaves, but it does reflect. A white piece of paper is reflecting all the different frequencies of light, but it's reflecting it in weird directions. And so what comes off of it, instead of it being a nice coherent image, is a reflection of stuff all over the place. So it's reflecting all the stuff in the room, and and pieces of all the room are reflecting at you, and it's all mixed together. When you mix them all together, what you get is the white color. So that's so when you understand that that's what's happening, then when you're looking at why is it that fog looks white, and why is it that you can see fog if water is clear, and a fog will create nice, perfectly clear water, right?
See water vapor from a steam kettle.
Yeah. Why do you see the water vapor though if water is clear?
Yeah.
That is because of the same principle. The light is no longer traveling straight, it's deviating. And because it's deviating, what you have instead of a nice image is light going all different directions, and the light that hits you is coming from directions it shouldn't be coming from. And so what you see is a mixture of light instead of a nice image, which is all of them all aligned and going in the same direction. Instead, what you've got is this just a bunch of light from a bunch of different directions, all just hitting your eye. So that's a completely different way in which the reflection is basically screwed up. So the same thing would be true of these cavitations. What's happening is it's just making it so the light is no longer traveling through the medium properly, and it's instead deviating, and it's no longer coherent. We have some questions here I need to look at. Let me take a look at these real quick. What's the point of this? Whether a steam engine is so efficient that mankind does not advance for another century? Let's see. Okay. The reason, the point of this is that whenever what we're talking about here is looking at physics. There's all these failures occurring in physics. If you've been keeping up with it, there's the vacuum energy catastrophe, where the difference between prediction and the actual experiment is a larger difference than one atom in all atoms in the universe. It's 120 orders of magnitude. There's problems with the standard model that have been discovered over and over through and things like supersymmetry, the versions of supersymmetry that have been ruled out. There's problems with standard candles versus the what's it called? Standard rulers in cosmology. So what you have are these failure points where we're pushing all the failure points of physics. And so the only way that you can make any advancement at a certain point, when you've got such good measurements, we've got so many good measurements that are obviously extremely accurate to a great extent. So how could you have any revolution? And revolution has been called for in physics. It's said it's necessary. One of the ways that you can try to have revolution is just by tweaking little things, right? And you feel like if you got really precise measurements that just a little more tweaking will get there. But the thing is, what if instead of just tweaking, what you can do is just take your whole thing and look at it from a different perspective that means the same thing, comes to the same answers through a different way. And basically you realign things so that you understand it in a different way, so you can extend your ideas of it in a different way. Because here's the thing, I explained this a number of times, and that is that there are truths within limits that people don't understand this idea of truth within limits. And that is, there's a tribe in Papua New Guinea who, what they do is they go and they pray and sing to the fishing tree. And if you go and watch them, then they actually gather fish after doing this prayer to the fishing tree. And so what they have is a type of empirical science. Now, right now you're going, what, wait, no, that can't be right. But that's because I haven't told you all the aspects of it. And that is what part of their prayer and singing and dancing and all of the ritual to the tree, which let me kill your sound here for a second, is that they beat a root into the water from the fishing tree. And that root has a neurotoxin in it. And that neurotoxin is only deadly to fish and not to humans. So they can then gather the fish. And what they have is basically an idea that is, it's replicable. They can use their idea of the spirit of the fishing tree, this concept of the behaviors of the world around them, to reliably produce results that are useful to them. So the thing is, it is an analogy to the truth. In other words, the spirit of the fishing tree is a truth within limits. And here's the thing: a truth within limits can even be extended sometimes. So, in other words, they could take the spirit of the fishing tree thing and maybe burn some of that root, because it turns out that neurotoxins are actually toxic to insects as well. So there is a way in which perhaps this neurotoxin that is toxic to the fish might actually be more toxic to bees than just regular smoke, and maybe it would actually be more effective for them in gathering honey. So once again, here it's the fish, and now they could extend it to, well, it's the spirit of the food tree. And so they could try to extend it that way. And so what they would have is, once again, empirical results that are reliable over and over. Every time they test it out, they get results. But the thing is, if they then try to take that root and burn it and, and try to catch a water buffalo with it, they're going to get run over and killed. So there's a limit to the way in which they can extend their model. Their model of the universe, of the spirit of the fishing tree, is currently a workable model that gets them reliable results. Understanding this idea that you can have your understanding of the overarching results that you're getting can be an analogy to the truth is critically important, because all throughout science we have things that are called virtual particles right now. And what a virtual particle is, well, the best way for me to tell you about this is what's called the phonon. The phonon is a virtual particle that happens in mechanical sound waves in a crystalline lattice. So the thing is, it has all the typical quantum mechanical behaviors, but it doesn't really exist. Everyone knows that a phonon, while it's a quantum, it is a discrete particle that you can calculate with all the normal ways that you calculate things in quantum physics. But the phonon is literally only there as a mechanical vibration in a crystalline lattice. In other words, it's just a way we're dividing things up based upon some interesting ways that the particles in the crystalline lattice work together to give us borderlines that require transitional energy levels. In other words, there's a point at which it'll reflect off, and there's a point at which it'll actually transfer through. So understanding that we have analogies to the truth that are useful, that's already part of science. And there's already all of these different things in current particle physics that are well known to be their analogies to something that's occurring. So the point here is that the only way that you can really have a massive revolution in physics, which is at the basis of having a revolution in physics, is what will get us some very big differences in our energy efficiency, our energy use. Basically everything, we're killing ourselves over, climate change, all of that ends up coming down to, if we were able to have this large revolution in physics, then we might also then have a large revolution in energy and maybe be able to, not kill ourselves. But the only way you can have a revolution is within the constraints of what's already occurred. So it has to be an analogy to in other words, it has to work within the structure that's already there. In other words, you have to be able to still reproduce relativity. You still have to be able to reproduce everything that we are already doing. And that seems impossible when you know how precise certain results are. But then when you find out that there's this 120 orders of magnitude error here, there's a huge error there, and well, we're just going to ignore that. You're going to not look at that. And there's all these errors happening in physics. That tells us, hey, we've got errors all across physics, huge, enormous errors all across physics. That means we got super precision working out perfectly and huge errors at the same time. What does that mean? It means that there's probably an analogy that we've got. Our total perspective about particle physics, our total perspective about modern physics could be entirely wrong. And if there's an alternative one that works, then that's the way that we need to go. And so that is basically what this is about, is that there's this alternative viewpoint that has actually been there the entire time. This is not something I've just come up with, but it was there and workable, and just it was lost to history. It's basically kind of lost history. So that is what this is all about, is that the ether is real, and that makes it a way in which we can completely revolutionize the entirety of physics. And there's a bunch of other comments I need to go through here. So let me do you mind if we continue to go through some comments here, Jerry? I'm sorry.
Sure. Yeah, absolutely. Yeah.
Okay, cool. I'm sure you've got other questions and stuff that we're going to cover. All right. So space-time, when you're not moving space, you're moving time. The less you move, the shorter your length. It's really just a speed graph. Well, there's a little more complexity to that, but I appreciate the sentiment. I will get more into the whole idea of a Minkowski diagram and things of that nature here with Jerry in a moment. Let's see. Standard model is mumbo jumbo. That is true to a certain extent. There's been some huge. Here's the thing. It's just like the spirit of the fishing tree. It is correct within limits. In other words, it is undeniably correct within limits. It is undeniably correct that when they do their prayer to the fishing tree, they receive fish. And if you were to try to tell them there's no such thing as gods and there's this thing called a neurotoxin, they'd look at you like you were just a freaking crazy person, because it's like, look, I do this every day. This is how I eat. My survival depends on the spirit of the fishing tree. You're a nutcase. Stop telling me about, what did you say it was? Neurotoxins? You're telling me there's weird things in my head. Ooh, so the tribal people there are going to look at you like you're a nutcase if you try to tell them, and it won't be useful to them. You'll just confuse them trying to talk to them about neurotoxins. How's it going to be useful in their lives? The spirit of the fishing tree is actually useful in their lives. It's doing something for them. And so the same thing would be true of misconceptions in science. So mumbo jumbo, that's kind of a relative perspective. We've done a lot so far. We've been able to accomplish a lot with what we've got. It's just now what we're talking about is how do we extend it? And that is re-understanding it from a perspective, from specifically the classical perspective is what I'm doing, is going back all the way. I go back 200 years in history and find the points at which where we could have gone one direction, we went the other, and it's still the same mathematically, because that's the important part. It still needs to be the same mathematically, and that's all I'm talking about. I'm not changing the math here. I'm changing the interpretation. So let's continue forward here. Are you saying cavitation bubbles are atoms? No, I'm saying atoms are cavitation bubbles. There's a difference there. So in other words, there's the idea of the ether, and then what the idea of particles, not just atoms specifically, but particles, especially like, for instance, electrons. There would be cavitations in the ether. That's how that conversation got started about cavitations. Cavitation, yes, cavitation in ether, correct. Ether as structured bubbles, correct. Structured cavitations. There is the interplay of waves with vortices, and there's something called wave vortex duality, where a wave can pump a vortex, and a vortex sheds waves. So the wave vortex duality is part of fluid dynamics. Is fairly well known in fluid dynamics. Unfortunately, a lot of people who are in other fields are not aware of wave vortex duality and how useful it would be in conceiving of atomic physics and all these questions of various dual slit experiments and things of that nature. How that understanding would help us understand wave particle duality is instead as wave vortex duality. Let's see. Thoughts on Michelson, Morley, and misinterpretation of results rather than non-results. So the Michelson-Morley experiment actually was non-null. Now you can look up Michelson-Morley right now, go get you a piece of graph paper, write it all down. And what you'll find is that so long as you are rational and you think of the fact that, okay, if there is a temperature drift, in other words, if there's a constant change, where once they move the interferometer 360 degrees, that that the starting point has ended up in a different place, then you have to, of course, correct for that temperature change over the full cycle. If you simply add just a simple temperature correction, you yourself can go right now on Wikipedia, get Michelson's original results, and what you'll find is it creates a graph that is a dual sine wave of results that exactly match what we expect, but it's just at a different speed. And if you calculate the speed that he got a speed somewhere between 8 and 12 kilometers per second, which is roughly 1/3 of the expectation. Why they report 1/40th of the expectation is because he had weird expectations. He expected that the wind would be coming directly from an east-west, and then also they had these problems where they would think about night versus day. So in other words, the different parts of the earth, if you think of the wind only coming from one direction, which is asinine, then you have to correct night versus day. And the problem is they were thinking of a jelly ether, but jelly ether had already been discarded long before the Michelson-Morley experiment. The idea of a jelly ether and there being one like rigid frame for ether is completely ridiculous. You have to instead think of the ether like the ocean. And so what they were doing is the equivalent of sticking a paddle wheel in the ocean and thinking that they could navigate from the United States to Africa. And you know, of course, because of all the currents and things like that, no, you never could. You have to think about the entrainment of the ether, of the water near the little paddle wheel you stuck down in your boat, things of that nature. So there's a lot of different problems about that. But when it comes down to it, it was not only non-null, it was not random, and it was a dual sine wave, exactly as expected. And then what you don't find out is Dayton Miller did tens of thousands of replications. He's the only one who actually replicated the Michelson Morley experiment, got the exact same thing over and over, tens of thousands of times, with where he had a double blinding procedure. He was one of the first people in physics to create a double blinding procedure where the people who were reading the interferometer didn't know, they couldn't see. They actually called it out to a guy in a different room as a bell went off. So that person didn't know what was happening. And this person never looked at anything but what was in front of them. And so they did all this double blinding procedure, thousands and thousands and thousands of experiments with different elevations, under different circumstances, with different materials, to make sure that there wasn't a magnetic effect. He changed the heat to show exactly what a heat effect would do and how it would change the data. He did all of these things, but unfortunately, a lot of people don't think that they think that a replication can be done with a laser. You can't do it with a laser. You have to do it with white light, like Michelson and Miller did. Michelson and Miller are the only ones who did a white light experiment. Everybody else uses lasers, and they also use a vacuum. You can't use a vacuum because the Lorentz contraction is real. The only way you can find Lorentz contraction is if there is a medium that is entraining the ether. So there's a lot of different issues there on the result of the Michelson-Morley. Was there something you wanted to say here, Jerry? It looked like you kind of had.
Oh, yeah. Well, I have written a few questions here to the side. I guess you can see that. I don't know if you can see that.
No. Oh, wait. Yes, in the chat. Whoa. Yeah. Okay.
Yeah.
Stuff for random private chat.
Sort of the main question you're mentioning about ether being fluid,
Mm-hmm.
that it's like ocean
Super
wave, or just like it has that plasticity. Is that, however? If it does, why would it push to cause length contraction? How would it have the pressure if it's sort of collapsible, or you know what I mean?
Okay, so ether is let me deal with some of the things here. Hold on, comments. I need to remove that for the moment. Okay, so what you're asking is, how would length contraction happen? Length contraction was actually developed by Heaviside. Was one of the first people to really develop the mechanics of how length contraction occurs, and he did this before 1905, and it was part of ether theory. And Oliver Heaviside is one of the people most well known for the development of the there was a few different people who were known as the Maxwellians. So Maxwell, he published a few different papers on electromagnetism, and we think of it as the father of electromagnetism, and we call them the Maxwell equations. But Maxwell never actually, the Maxwell equations that we use were not actually put in the finite format that we use them. Those were done by Heaviside, and it was his work. It was Heaviside, Fitzgerald, and Lodge, actually, who all worked together to basically pull together the much more difficult to understand work, which, in other words, there was a much more physically described set of things in Maxwell's originals papers, which were like, what were the names of them? There was two different ones. I can't recall their names at the moment, but so the point is here is that there was a lot of work that was done by them. And so electromagnetism is not just from Maxwell, but there were developments made by Heaviside and Fitzgerald that were critically important to explaining the Maxwell's equations. Some of the things that you don't know is that there was correspondence between Heaviside and, for instance, Kelvin, and I believe it was the correspondence between Heaviside and Kelvin, where he first, it may have been Heaviside and someone else. That'll be in my book. It's I've got it written down somewhere. You have to like dig through just tons and tons of history books. And there's a point at which he's describing the way in which the deformation of a specific object in a fluid, electromagnetic object in a fluid, would occur because of its movement through that fluid. So in other words, he actually described the mechanism in a mathematical way, the reason why a vortex in a fluid would be deformed to be a different shape. So what we're talking about is the deformation of particles, and that is what Heaviside described in his conversations with Kelvin. So when you're talking about the length contraction being physically real, what I'm saying is, why does a vortex move through the water? So say you're in a swimming pool and you make a little vortex, you do like this, and then it moves. Why does it move? If it's, why does that center move? Well, it's because there's a differential in the flows, and that differential will actually be expressed in a deformation of the vortex that you might not be able to make out, but the deformation of the vortex will actually be alongside that the motion of the vortex. So the point is, as particles, as vortices, as Kelvin's ring vortex knots are moving through the ether, there is a deformation to them that occurs, and a deformation to the surrounding field. Because you have to understand I have to mute you again for a second. So you have to understand that the borderline around an atom is not particularly real. In other words, there is what we think of as a field. So I'm gonna have to return back to the tornado analogy. So a tornado, you see, whenever you think of a tornado, I say tornado, you think of a funnel cloud, which you can see. And of course, a tornado is way bigger than that. In other words, it's when a tornado goes through an area, generally speaking, it's going to tear apart all the stuff nearby. It's because it's not just that borderline transition you look at, but it's air moving all the way around it. So even though you can't visually see the other parts of the tornado, they are still part of the tornado. And in fact, the tornado is just a focal point, a whip crack of two different storm fronts, their energy getting focused down into that one small vortex. So the tornado is actually a very extended entity. You think of it as an entity because you can see a borderline. It's your vision of the borderline, and that borderline is something real. It has to do with the relationship between the speed of the motion. A vacuum is actually created as something rotates. Whenever you create a rotation in a fluid, it starts to create more and more of a vacuum. So in the center of a tornado, the air pressure is much lower. And so there's a point at which that air pressure change as it is a gradient moving out based upon the speed of rotation. And that changes the relative humidity, which is why you have droplets forming in a tornado, because the rotation rate is changing relative humidity. And then you see the droplets in the air that you think of as a fog that creates the border. The border, however, it's not really real, is it? Or is it? That's the thing. You have to understand it's both real and not real, because it has to do with real transitions at a point at which, there is where water droplets will form. So there is a relative humidity point. There's all these ways in which the borderline of it is real and not real. And so you have to understand that the same thing, it would be true of atoms. There's a borderline that is real and not real. And the field around it is also just as much part of that particle as the particle is. And so that would be true of a tornado, and that would be true of ring vortex atoms as well. Let me unmute you now. I'm done explaining that part of it. Okay, so let's see if you didn't have let's see if we can answer some other questions that are in the chat here as well. Means model is wrong. I can't read them very well. I need to change the size of this. Live talk on the rather. I think you meant the ether. Yep. Let's see. The toroidal vortex model, fundamental power, Carl Kraft. Thanks. Okay, so yeah, what I'm talking about is a toroidal vortex model of fundamental particles, but unfortunately, all of those tend to descend. Hold on, let me mute you again. All of those models of toroidal vortices tend to descend from attempting to start too far forward in the process. In other words, they recognize all of these different behaviors that descend from Kelvin. You have to understand that like on Einstein gave a speech on Kelvin as the father of topology, and you have to understand topology actually came from his developments in the vortex atoms. That's where topology actually comes from, and knot theory. Knot theory comes from Kelvin's work on ring vortex knots, and all of those things are actually a part of like, for instance, okay, what was his name? J.J. Thomson. There's two Thomsons. Whenever you look in, if any of you guys actually start investigating history, when you first start dipping into history, you're going to get Lord Kelvin. The reason why you call him Kelvin is because there's another Thomson, because he's also Thomson. There's two Thomsons that are contemporary to each other. Thomson, J.J. Thomson, is actually a father of nuclear physics. He was actually Rutherford's mentor, I believe. But anyway, J.J. Thomson was the first person to ever create a physical reasoning for valence, and he did it based upon Kelvin's vortex atoms. But you have to understand, you have to travel back to an ether for any of these things to make sense, because, like as I said at the start of this video, this is about returning to classical ideas, which means that you have to throw away anything where you are allowing magic to be part of your idea. And people don't understand we've got 100 years of magic because we allowed ourselves to believe that a wave could exist without anything waving. That is a magical ideation, and it's an unfortunate part that that we just accept whole, just like any orthodoxy. We've all here's the thing: if you've been part of an orthodoxy before, you understand, having these ideas loaded into your head and having to take them apart. You have to both have been part of a fundamentalist religion and then defeated that within yourself to really comprehend how much ideas fed into your brain can be this like absolute automatic truth that you accept and don't question. And then later on, you're like, oh my God, I wasn't questioning this at all. And so that's that having that kind of perspective is very helpful. I'm kind of glad I was raised fundamentalist and was able to go through kind of being like, okay, that's not right. Because here's the thing, there are things like the idea of a wave without a medium. It's complete nonsense. It's magical thinking, and it's part of science today because of the telephone game, because you don't need to get rid of ether. Einstein in 1920 said space without ether is unthinkable. It's completely unrealistic. It's irrational. The problem is people don't understand how to make relativity fit with ether because they've forgotten the history. It's forgotten history that's the problem. It's still mathematically exactly the same. You still have relativity with ether because relativity, the Lorentz Transform, was based upon how ether and light work together. That's what it is. It's a mathematical model of light in ether. And so people, because the history has been lost, and specifically it's a one specific sociological event, that freaking Minkowski, if he had not just died prematurely, being everybody's friend and being Einstein's mentor, everybody lost their shit when he died prematurely, and that they had to, honor his 1907 paper when he only had 2 years to think about it. Guess what? People change their mind over time. They put out something and then they get a chance to think about it for a while. And had Minkowski had time to think about it, he probably would have gotten rid of the idea of constancy himself, because Einstein later on is railing against constancy over and over and over. And the thing is, even that is confusing, because what he's talking about is isotropic constancy, not the anisotropic illusion of constancy that Einstein himself did understand. But most people do not understand it today. They do not understand how you create anisotropic constancy, two-way constancy. They only understand the idea of this, isotropic constancy. So that's a long conversation that me and Jerry we're going to get to. I think we'll probably still get to it, but that's the thing. So yeah, I don't know this Karl Kraft person because I stay with historical physics, and I'm trying to stay mostly with just resurrecting those people who were the work of those who were the closest to modern theory. In other words, you take the people who are the closest to modern theory, the ones who developed the parts that actually contributed to modern theory. In other words, you have to understand all of their social relationships and how they influenced each other. And then you end up finding, these are mathematically equivalent theories. Like for instance, in quantum theory, Madelung showed that quantum physics can be recast in hydrodynamic form, like right at the very beginning of quantum physics. Yet nobody really knows now that you can have a hydrodynamic version of quantum physics. They don't know that, because it's you have to be really interested in the history. You have to do a lot of research, and understanding that it's mathematically equivalent is absolutely crucial. I have to keep getting back to that. Mathematically equivalent. It is a understanding of the data that is different and allows you to extend it differently, which is why, earlier, for some of you who may be new here, that's why I had that whole idea of the fishing tree and all of that. Let's see, go through some of these others. It says autocorrect algorithm rejects the existence of ether. It's true. I agree. It does. The same thing is true of a lot of things. Michelson model should be done in space outside the ether and trained by the Earth. So there can be a true just proof proof of the ether. Here's the thing. There have been thousands and thousands of Michelson experiments theoretically. And the problem is that people who are doing them, the scientists who do them, don't understand the requirements of the historical theory. You have to understand the requirements of the historical theory. And that is the historical theory, the historical ether theory that was relevant is a relativistic ether. And that's what's lost. So to understand how relativity works with an ether, you have to have the concept of the ether entrainment that comes all the way, it goes all the way back to Fresnel and Fizeau, or Fresnel, I should pronounce his name properly, but I'm never going to get that right. So it goes all the way back to Fresnel's prediction of the Fizeau experiment based upon his idea of how ether causes refraction. And he exactly predicted it. It came out to his predictions mathematically, and it was called the coefficient of ether drag. And now that relates directly to, mathematically speaking, to the, what's it called? Relativistic velocity addition. So there is an analogy to it in current science. But the only difference is just changing the way that what the mathematical symbols mean. In other words, what they refer to is all that you have to do for this to work in ether theory. But there's some nuances here that I don't want to get too far down that rabbit hole, because it ends up getting too detailed, and that's just going to throw everybody off. Because the whole point here is to have like a conversation, a layman's kind of conversation, and we're getting too much of the details. I'm sorry about that, but that's in papers and things like that. Does this mean Lorentz ether theory is consistent with ether drift? Ether drift experiments. So Lorentz ether theory, actually, he had sort of an electron theory. So you actually have to take Lorentz's work and update it with Poincaré's work. So in other words, Lorentz did a publication, then Poincaré did some corrections to Lorentz's work, which are directly and perfectly equivalent to relativity. And there's actually a historical point at which some people claim that they purposefully didn't publish Poincaré's work because he was French, and so there's this rivalry between France and Germany at the time, and so they didn't publish Poincaré's work before Einstein's, and that Poincaré should have actually been given primacy for special relativity. But his theory was specifically an ether theory. In other words, Poincaré's work was an update of Lorentz's, in which he throws away Lorentz's work in the electron theory. So Lorentz had some work that he was trying to extend, and Poincaré, kind of threw some of that away and corrected it. And that's why it was called mathematically indistinguishable from relativity, is what people have called it. However, it is an ether theory. So this is what I'm talking about here, is an ether theory that Poincaré gave us. And if it's theoretically mathematically indistinguishable. It's not, however. I actually do show how it can be mathematically distinguished. It's just very complicated. That's all. It's just complicated. But it is mathematically equivalent in its outcome. And that's the point, is then the outcome is the same. And so what we're talking about here is a revolution in our conception of it that can lead to a revolution in the future. In other words, the way we extend our model. As measured by the Michelson-Morley experiment. Okay, so in the Michelson-Morley experiment, the original Michelson-Morley, the 1887, I realize there was one before that, but the one that everybody thinks of, there was a non-null result. And it was not, even if you took an overly simplistic view of it and didn't look at the fact that it's nonlinear, in other words, the relationship between the actual speed measured and the size of the difference between the two different the phase difference. Basically, when you look at the difference, the phase difference between the two beams, there is a nonlinear relationship between what speed that means and how big the measurement is. And so a very, very small difference will still give you a fairly large speed because of the fact that it's a two-way experiment. So for instance, in the original, in the 1887 Michelson experiment, the speed that you can calculate yourself, we can go to the data right now, it's still available out there on Wikipedia. The speed he actually got was between 8 and 12 kilometers per second for the ether wind. You know, it was coming from a northerly direction, not from the east and west, as he, and that's why it gets misreported. But it was coming from a northerly direction. And what he was talking about was the size of the measurement instead of the speed that it means. So the speed that it means versus the size of the measurement, not a linear correlation between the two. So understanding that is very important. But yes, the original Michelson Morley is not null. It doesn't even fit with the 5% idea of null. It's just not null. And it's not only that, it's not random. It shows the dual sine wave of readings that you would expect of an ether wind in that experiment. And all that aside, tens of thousands of replications by Dayton Miller, and it's only a replication if you use white light, and only a replication if you have it not in a vacuum. You have to have, for it to be relativistic ether, you have to have a medium, which we normally call a medium. In other words, you have to have a gaseous medium to entrain the ether for there to be basically the Michelson Morley experiment, the Dayton Miller experiment, actually is a one-way speed of light experiment, is what I'm saying. It actually is a one-way speed of light experiment that has successfully shown that there is a difference in the isotropic speed of light. So there is that light speed is anisotropic. The original Michelson Morley and all of Dayton Miller's work all prove that, is actually what I'm getting at here. Let's see. It's pretty incorrect understanding there. Correct. That's true, Ash. Let's see. Great, thanks, Max. I have worked for well over a decade to make sure that so many people. I've been giving away basically 90% of the book just to make sure people were ready for this, because just 15 years ago, people would really attack you for daring to besmirch the holy name of Einstein. It's like, no, I'm not even disagreeing with it. But so it was really difficult. But thankfully, over the past 10 years of lots of hard work, people started to actually accept that, hey, maybe we should actually look at things in a slightly different fashion. Maybe we don't have to be, perfectly orthodox, and we can, conceive of it and come to the same answers in a different method, and that be okay for science. Yeah, it's a little, call me crazy. Let's see, magnetism. Fundamental particle of matter. How's the phenomenon manifest hydrogen from black hole jets? How does that work? I'm gonna stop here and get back to Jerry, because I'm leaving Jerry on the line. Sorry, Jerry. I'm gonna answer this one final question, then we're gonna get back to your questions. What is the fundamental particle of matter? I'm saying, as I pointed out earlier, that I don't necessarily think there is. Well, okay, here's the thing. I think that perhaps at the Planck level, there may be particles of ether. I actually have an idea for their shape. But I think that probably below that it's also continuous. So I think it continues back and forth between continuous and discrete over and over repeatedly down at smaller and smaller scales. I think there is something probably below the Planck scale as well, which is it's just crazy that there would be anything below that. But I personally don't believe, and this is just opinion. You see, at this point, there's really not adequate evidence to say in any kind of, reasonable way. But it is from what I have seen, I believe there's probably a particulate type of substance that's locked together, sort of like gears in, and I have reason to believe why it acts like a kind of like a crystalline. It acts like a liquid crystal. In other words, there are some liquid crystal-like properties to the way in which ether behaves, and so that would mean that there's some sort of cellular type of structure. And this was all back in the early, from 1890 to 1905 era. There was lots of scientists looking at these various, versions of a foam or of like cells as part of the ether. So this isn't even me speaking, talking about the various cells. These are just this is the historical way in which ether progressed. However, it did reach a pinnacle in 1909 that nobody knows about with the Kosarat brothers and micropolar elasticity. So I'll just leave it there. But how does how does a particle of matter, how does matter work? So I'm talking about ether as particle. Matter is a phenomenon, sort of. In other words, it is the capture of energy. It is a flywheel of rotation that feeds back upon itself. In other words, the waves, the speed of rotation allows the waves to travel in a loop such that energy is captured in a location through rotation. So what you have is a rotational entity that is both waves and vortices because of wave vortex duality, and that is what creates what we think of as an atom. So in other words, there is a very specific pattern necessary to create any given particle of matter, like a hydrogen atom. And what a hydrogen atom would be is so you're saying that hydrogen comes from black hole jets? That's actually news to me, but it makes sense, I guess. So the way in which you would create a particle of matter, which I'm not going to get too much into here because there's some people who don't want me to talk too much about that, is basically by having the right resonance and pattern to the way in which the ether is being rotated and resonated. That's the best I'm going to do here. I might put it in book form, but there's some people who would rather not talk about that, so I'm gonna skip right over that. Okay. Anyway, so let's get back to you, Jerry.
Well, all right. The idea that there's length contraction that's physical.
Say again.
The idea that there's length contraction that's a physical. I mean, with the apparatus of the interferometer. I mean, if any type of measuring device shrinks with it,
Mm-hmm.
how can you tell? Can you tell visually? I mean, to what degree is it shortened?
Right. The degree that it's shortened is determined by Lorentz contraction. So in other words, it is a calculation. So what we have in the idea that Lorentz and Fitzgerald and all of those who were actually part of bringing us electromagnetism from Maxwell, in other words, in Heaviside, people don't mention Heaviside nearly enough, is a mathematical model for how much it must be shortened, but it's specifically a mathematical model of an illusion. And that's why this concept is so confusing to most people, is because what's going on is that reality is creating an illusion. Now, this seems unrealistic to a certain point unless you do something like study the way the Doppler effect would work. And so I'm going to go there first before I return to this illusion. And I'm going to mute you for just a second. So, for instance, if I wanted to try to, let's say we had a perfect medium. And you know that the Doppler effect in sound, because we do need to stick with sound here to keep from confusing anyone. The Doppler effect in sound has two different ways in which it could occur. And that is, you can go through the medium and run into waves more frequently. It's like, say, this is the emitter. Run into waves more frequently, and that changes the frequency up, or run away from them so they can't catch you, and therefore they will hit you less frequently. That's one way in which you're going to get Doppler effect. Another way you're going to get Doppler effect is through a moving emitter. And that is, you're inscribing waves into the medium closer together before they can escape in this direction. And you're inscribing them into the medium further apart as you're moving through the medium. And that creates a lower frequency. So there is lower perceptual frequency and higher perceptual frequency. That's just a perception because you're moving through the medium. And then there is also actually inscribed into the medium differently. These two things are exactly the same in you're just hearing a higher or lower frequency. In other words, it's very difficult to determine the difference between these two. Not only that, if you are in motion and there's two people in motion, let's say, and we're going to have to ignore all the fact that wind is making the air go all over the place and causing other types of effects, but trying to determine who is moving only by frequencies. And by comparing frequencies, Doppler effect between two moving people will actually hide itself. And you can't tell if it's real Doppler effect if you don't know where the medium is. In other words, you don't know where air is. You have no ability to stick a little spinny wheel out and measure the air. So you just don't have that. Then if you're two people on like trucks moving along and you try to figure out if you're moving or not based upon the Doppler effect, you're not going to be able to figure it out, because if you're both co-moving, the amount by which you're changing the distance and the way in which you're reading it, and this is something I'm relying on people to actually look into themselves, is that it will hide it. So in other words, nature does create these illusions. In other words, it make it where certain effects will be hidden from you under certain circumstances, and that is particularly true of the Doppler effect in a physical medium. And when we're talking about mechanical waves. So they knew this, of course, and they're talking, these people are very well versed in wave phenomena, of course. And so they knew this when Fitzgerald suggested that what was occurring was a shortening. What he was talking about was an illusion. In other words, that he said maybe nature has this illusion that would be kind of like the Doppler effect, like I just described, that there's this weird compensatory illusion. And that's the thing. No matter how fast you go, it compensates by a precise amount that perfectly hides the illusion from you. And that's what we're talking about with the Lorentz transform. That is what it was designed to model. That is what the math was completely created to do, is to create an illusion. In other words, mathematically model a physical illusion. Yep. I mean, unmike you.
Well, often, I've read that that both Lorentz and Fitzgerald didn't. That they were trying to prove why, because it was widely held that the Michelson and Morley experiment was invalid. There was no results. And then from what I'd read was that they arrived at length contraction and mass increasing with velocity. That was their way of explaining why the experiment had failed to detect the ether.
Right. There's a difference between invalid and null. In other words, it was widely held that it was null.
Oh yeah,
so yeah, they were under the impression that it was null. That's correct. And here's the thing: that is a serendipity. In other words, that the fact that they thought it was null is actually a good thing, and I'll explain more of that later. But the point is, assuming that it is null, basically that's what they were describing, that it does create this null experiment, and that's why, yes, all two-way experiments in a vacuum should be null according to this relativistic ether theory that Lorentz was first working on. Okay, because of this compensatory illusion that they're mathematically modeling. So I'm actually not. If you've got some sort of reference on the mass thing, that I've never heard that anywhere before. You're the first person who's ever said that to me. And that theoretically they had the idea of increase in mass. I have not
read this book by Isaac Asimov.
He may have been incorrect.
It's a collection of a lot of smaller books.
Mm-hmm. So he may have been incorrect about mass increase coming from them. I don't know. I haven't run into it yet, but I'm definitely going to be on the lookout for that, because I think the mass increase only came as something after general relativity. That was my impression. But anyway, yes, they were trying to explain a null result. And so they were mathematically modeling a null result, which means that there's a compensatory illusion that is mathematically modeled. And so remember when earlier I was talking about the swimmer that she travels 20 miles an hour, and you've got stakes on the ground that are, 10 miles apart, and then the river is 10 miles wide. And then if there is a mathematical way to determine how much extra water he's going to have to swim through to go straight across. In other words, he's going to be swimming at an angle the entire time because he's kind of swimming partially upstream, and he's going to go perfectly straight across and straight back. He's going to be swimming at an angle the entire time. That means in the water, according to him, he's going to travel a further distance than 10 up and 10 back. That distance is a specific amount. It just so happens, because I set it up to be half and I remember these numbers, that distance is going to be 23.094. Okay. And so instead of just 20. And then if you simply take the stakes in the ground along the 10-mile path upstream and back, and you reduce it to 8.66 miles, then his round trip up and back will also be 23.094. So you see, what they're doing here is making a type of illusion. And let me describe this in another way. Instead of with a swimmer, what I'm going to say is I'm going to take a flatbed truck, and I'm going to make it out of some magical material that shrinks an amount relevant to how much air wind is going across it. Okay. And it's going to draw up as wind goes across it. And the faster the wind goes across it, the more it draws up. And it's going to do this according to the Lorentz transform. Actually, that's the mathematical formula by which it's going to do this. In this experiment, if I set it up to be this whole thing made out of this material that can shrink, and I have one piece of it sticking out to the side, exactly 10, and one going up the direction that the flatbed truck's going to be moving, exactly 10, and it can reflect sound. Then, and if of course the contraction has to be only in one direction, in the direction of travel. Then if I set this truck moving at half the speed of sound, then even though, and then let me give you one final piece. It just so happens that microphones can also double as, speakers can also double as microphones. So if I wanted to make a chirp, the chirp will go out and reflect back and come back at exactly the same moment. And I'm going to compare that. Now, if I set that truck in motion, because it happens to shrink that exact right amount based upon the wind, even if it's in motion at half the speed of sound, those chirps will still arrive at exactly the same time, so long as it shortens by the Lorentz transform. In other words, the material, so long as it shortens it up by that exact amount, the total round trip at half the speed of sound would be 23.094 out and back and 23.094 upstream and downstream. But here's the thing. So all of that aside, this means that there's also a time component. Now remember that, so how do you come to the whole time component of relativity? That was also there as well in ether theory. And that is the idea that time is mediated entirely by change. In other words, time is nothing but change. That's all it is. It's just things changing. And that all changes are mediated by signals having to travel through the ether. And those signals always travel at one speed, because the speed of a wave is just a property of the substance the wave is traveling in. That's all it is. A speed is a property of it. In other words, it's a combination of density and rigidity or bulk modulus. But the point is, it's a property of it. So it looks like you were about to ask me something now.
Well, there were a few things. One of the most recent ones about. I'll just read this. Something I haven't had a good understanding of is what was the exact purpose of the experiments with the interferometer. What results did they did they expect? And if the experiment had turned out perfectly in their eyes, what would that have told them? And what does that tell us today? Is it like measuring how fast we're going through the ether, like compared to the Earth, the sun, the galaxy?
Okay, so yeah, what Michelson's expectation was not a good expectation based upon the ether theory that was relevant to the period in which he did it. He did not. Here's the thing: we didn't have the internet back then, so you could be behind on what ether theory was. As a scientist, you could be behind on what ether theory indicates, and especially since they're still developing it, you can have a preference as well. So there was two different kinds of ether available at the time. There was the jelly ether that Kelvin was still supporting right up until I think it was 1889, even that Kelvin. And Kelvin he's this major contributor to all of this stuff. And his main problem was that he supported the jelly ether because that was the older version of it. The idea of this kind of a squishy, solid sort of thing that stayed stationary. However, there was McCullough's ether that had rotational elasticity. And until 1889, when Kelvin proved it could be physically real, because Kelvin's the one who actually proved it could be a physically real thing, people thought of it as too non-physical. Rotational elasticity seemed like weird non-physical thing to people, and they wanted something that made sense physically, and they didn't, they wouldn't accept something that was like we do today. We had like a field. What's a field? Oh, it's a field. It's numbers. Like we accept these things just kind of carte blanche without any need for any real mechanical understanding of how that works in physical reality. We just accept it. But back then they didn't accept that ever. They thought that they would, you're out of natural philosophy society. So they wouldn't allow that sort of thing, which is why he, kind of stuck with the jelly ether himself. But then he actually wrote a paper and created models. And in 1889, it was, I think it was on the hydrostatic adynamic constitution of ether, in which he showed a physical model that could represent McCullough. I mean, McCullough was actually, I think, 30 or 40 years earlier, had described birefringence. Oh God, I can't say that word. Birefringence. I think that's right. Wow, it sounds weird. Through, like, there was feldspar, and there was these different things that cause an effect with light, and he had explained it through a type of rotational ether. In other words, the elasticity was rotational. And she's giving me. Yeah. Okay. So somebody's signaling me that I need to meet you again. So rotational elasticity was then proven to be physical by 1889. That's 2 years after the Michelson-Morley experiment. So at the time of Michelson's experiment, he was thinking he could use this jelly concept to measure the speed at which our solar system was traveling through the universe. Now, I don't think they actually had even any inkling that there were other galaxies at this time. So it's just how fast the universe, because they assumed, oh, well, of course the Earth is in the center of the universe, so we have to be traveling through it. So therefore, if the ether is just slipping past us, then it's going to be going some speed that we can measure. Well, we already know that the speed of the Earth around the sun is around 30 kilometers per second. We know that because of the thing with the moons of Jupiter and all that at the time. So they knew that. They didn't really care about that as much as the speed that the whole solar system was moving. But it was based upon this assumption of a jelly ether, stationary, no currents, no local anything. And that just simply isn't how the ether works. And that wasn't how modern ether theory at the time worked, because there were plenty of other people who were working with a model of ether and electromagnetism. Even all of Maxwell's descriptions of how the ether worked were based upon these rotational structures. Everything that Maxwell described, he said that the ether works like wheels and pulleys. And so he was talking about that it was all gears, wheels, and pulleys. I think it was something like that. I have to find the exact quote. I put it in a few different places, but so the idea he was describing was a rotational ether, and that's what that's why we eventually arrived at that Maxwell was right, that there was a rotational ether. But then even Fitzgerald had to use McCullough's work in working with Heaviside to give us all of the finished work of Maxwell, because there was a finishing part that Maxwell actually never finished, and that's how we have the Maxwell's equations through Heaviside with the help of Fitzgerald. They work very, very closely together. Yes.
Yeah. Well, sort of off topic. You just mentioned. The second postulate of special relativity, the constancy of the velocity of light.
Uh-huh.
Do you have any idea where that is from? Was that from Maxwell's equations, or I've read that it's from Maxwell. I've read that it was from Einstein personally. I don't know where it was from.
It comes from now. 20 years ago, people once again didn't really know a lot of the issues with between Einstein and the relationship between him and Lorentz. But there's a quote from him that's like, when I made the theory of special relativity, I was well aware of Lorentz's work on the Michelson-Morley experiment. There's a direct quote from him where so what he was working from was the Lorentz transform. The thing is, if you just take the Lorentz transform, so there's kind of a shut up and calculate sort of way you can do things. And that is, you can throw away theory and just see what numbers tell you. And sometimes that can be very useful and helpful. Sometimes it can lead to a confusion. And in this case, it did lead to some level of confusion, because when Einstein was saying you didn't need to think about the ether, he was right in a certain way. Because if there's this illusion, and you can't theoretically pierce the illusion, then what good is it? And a lot of people are going to ask, a lot of people do ask me this. Well, if it's mathematically equivalent, then it's useless. No, it's not true, because there are subtleties and ways to arrive at it through different means that are more complex, that give you more information and allow you to expand your model better and to have more accurate experimentation. In other words, the way in which you guide your experimentation is very, very about the vector of the search pattern, the area that you look for the future development of your theory is based upon theory, not just the mathematical outcome. So what Einstein was doing was seeing that, okay, if you assume we are traveling through the ether, and then you are assuming that that light will seem to travel the same speed up and back and across the interferometer. So in other words, a null result on the interferometer means that the light, even though you're moving, still seems to be going the same speed, because if it goes out to the left and comes back and goes upstream and downstream and it comes back at exactly the same time, then that's the same speed. So in other words, you have this thing where light seems to travel the same speed no matter how fast you are going. And so that is, the light travels the same speed in all frames of reference, which is the constancy, the second postulate of special relativity, is that light travels the same speed in all frames of reference. But that is another way of saying that the Michelson-Morley experiment, no matter how fast it goes, if you have this compensatory illusion of shortening it up, that's just the right amount, then it's always going to give you the same that exact result. In other words, that the light traveled the same distance both directions. It came back at exactly the same time, even though you're in motion. In other words, even that illusion that I was talking about with the trucks, because it shortens, it actually creates this illusion. However, there's another part of the illusion I want to talk about here in just a second. But does that make sense?
Yeah. They sort of cancel each other out as far as does that mean that the velocity of light varies from from one inertial frame to another?
Absolutely, but it only varies in one direction, not in two directions, and that is because our measuring devices are shortened and our time is dilated.
Would it vary so much that if you're going almost the velocity of light, that if you're about 5 miles per hour away from reaching the velocity of light, would
there be distortions?
What about the maximum possible velocity? Is that a valid theory?
So how would this max velocity? And that is where Heaviside, when he was developing the idea of shortening, in other words, how physical shortening occurs in atoms, as Heaviside was developing that with Kelvin, he was actually talking about the max, reaching max speed. In other words, what would occur, and talking about flattening out into plane figures, and there were questions like that already going on, and that was I think it was early 1890s. So he was already discussing that idea. But hold on a second. So what exactly are you asking again? I'm sorry.
About well, I mean, if you're going almost the velocity of light, I mean, so that's relative to the stationary ether,
right? It would definitely be relative to the stationary ether. Okay, but the one thing. Okay, let me give you another piece of the puzzle that I think will help, because there's also a time component. Remember how I said that it's 23.094? Well, that means that there is additional time for that experiment to elapse. Normally, it should only take if it's a distance of 20 and total going 10 up and 10 back in both directions, then the total experiment taking additional time should be measurable in some way, right? It does have an effect. It has an effect on time, and this was something that Lorentz was aware of as well. And that is because it takes longer to elapse. Every single atom, every single particle is having, if change is mediated by these waves traversing a medium, then because it takes longer for one atom to have any communication or impact with another atom, it takes an average up and back, an average back and forth. Then what you're going to have is that additional time for the experiment is an analogy to the additional time required for atomic interactions and intermolecular interactions. All of them are going to be governed by this additional time. In other words, there's more time for the signal to go between them and back. It's going to be 23.094. It's going to be basically the Lorentz transform additional time for any interaction, any change to occur. So therefore, time is actually slower as matter travels through the ether, because it takes longer for the light to go between particles. And it's on average, it's that amount, because that's the amount that things shorten. And that is directly related to an electromagnetic reasoning for there to be a deformation of these particles.
About the constancy of velocity of light. It had been my understanding that was sort of why space and time are relative, like that was why the idea was even thought of, the relativity of time and space, because they sort of compensate for the amount of time that when there are two, like the relativity of two objects, if one's so-called stationary, then the other one is traveling at a great distance, that that to either one.
I think I understand what you're saying. You're talking about relative simultaneity. Like there's this great little thing from PBS where they have a guy sitting here on Earth on a park bench and an alien on a bicycle all the way across the universe. And relative simultaneity says that just that alien's speed on his bicycle, either going towards us or away from us, determines by hundreds of years how much what actual moment on her Earth he is simultaneous with. And so there's this idea of relative simultaneity and all that, and that does relate to constancy, but all of that is an interpretation that comes specifically from Minkowski space-time. In other words, it only happens when you conjoin space and time into one thing, and that happened because he believed that light speed is isotropic, and that happens. The reason why you believe light speed is isotropic instead of anisotropic is that instead of believing that it's an illusion, that is a compensatory illusion that Lorentz was modeling, which is exactly what he modeled, if you believe the exterior of the illusion instead of knowing that there's an underlying mechanics to the illusion, if you simply believe the exterior and say nothing about the underlying mechanics, then you can't say, oh, well, we've measured the one-way speed of light. So we've measured the one-way speed of light. Well, if you can't measure the one-way speed of light, and actually you can, but if you haven't, let's say you haven't measured the one-way speed of light, and everybody believes to this day right now that we haven't measured this one-way speed of light, but that's excuse making based upon their belief in relativity. But I don't want to get into that at the moment. That's
the twin paradox and such. Just time relation.
So the twin paradox doesn't occur in a relativistic ether theory, and that is because there is also relative time contraction and length dilation. So in other words, whoever is most, let's pick one of them to be stationary with the ether to just make it not complex, because both of them moving with respect to the ether also has an effect I won't really get into. But let's just talk about one of them moving with respect to the ether and one of them stationary with respect to the ether. The one that is stationary with respect to ether will have the normal time, and the one that is going out away and coming back, they will absolutely be the one that is time dilated according to ether theory. So but the thing is, what they will experience is they will believe, unlike current relativity theory, they won't believe that the twin on Earth is actually the one who is aging less. They will believe that the one on Earth is aging faster, because they will see the twin on Earth as being time contracted and length dilated. In other words, they will have a compensatory understanding through the math, and that's the thing that's missing when you use Minkowski diagrams. There actually is this kind of a shadow calculation of relativity where that people don't do, that they and that's what causes the twins paradox, is because you do not pick a preferred frame. Actually, every resolution of the twins paradox is the choosing of a universal frame. And Minkowski, Einstein, of course, he said, we have to be rid of constancy. Constancy is no longer valid as of general relativity. Over and over, like I said, 5 different quotes from him in his notes about constancy being crap that we have to get rid of. What he meant was isotropic constancy. He did not mean the compensatory illusion that I've described to you. That is real. That is what's really occurring. And that's why relativity is valid, is because there is a compensatory illusion that occurs. But the idea of constancy, which means that light travels the same speed in all directions, is what the confusion is. And understanding these two things is very difficult. Understanding that these two things come out the same, the compensatory illusion versus the way that people describe relativity to you, these two things, they're very, very similar because the eventual outcome is the same. But understanding the difference lies in this anti-relativity. And that is that there is that the twins paradox does not occur because if you know the ether theory, that there is not just time dilation and length contraction occurring to the moving observer, but apparent time contraction and length dilation occurring to the stationary observer from this person's perspective. So in other words, it makes sense. There is no twins paradox at all.
A while ago, I read about mutual time dilation, where if there's two, like say there's two spacecrafts in outer space, and whichever one is going faster than the other, you can't really tell because, well, to me it seems that you need another object to go by in reference to say, well, I'm going this fast relative to this, however that is. However, though, like when you somehow view the other, like there's another astronaut or another spacecraft, that you see that somehow you see that their length is contracting and such. You see those effects, except that within your own spacecraft you don't see any difference. However, though, like say they have synchronized watches, and that their times are different while they're traveling fast relative to each other. And then when they meet up, their watches are synchronized. They stay synchronized when they meet up because the effects cancel each other out. However, that's different from the clock on the plane experiments, and as well as the thought experiment of the twin paradox. That you know what I mean?
Okay, no. Here's the thing: a person who in this ether theory, because of the fact, remember I was saying that it takes longer for change to be mediated by waves in the medium in between particles. So everything occurring in your brain, everything occurring between your cellular processes, the electron transport, as part of cellular processes, all of those things mediated by signals between atoms, between particles, and even inside the atoms themselves are all being mediated by the speed of light. Okay. And so the thing is, and not just the speed of light, but the distance light has to travel. So if ether is going across these things, then what's happening is that the distance light travels is actually greater. So it takes longer for change to occur. Therefore, time is really slowed for someone traveling through the ether. So in other words, if a person is stationary in the ether and another person is moving through the ether, the amount of time that the person has and actually experiences, the moving observer will, just like relativity says, they will be slowed. In other words, they will have had a slowed experience. However, they will calculate, because they know that it's an effect of the ether, that this person was stationary with respect to the ether. Therefore, they have the preferred frame. Therefore, they will know that this person experienced according, relative to them, the opposite of what they experience. Because here, let me give you an example, because we've been kind of circling around this. I'm going to give this example, then I need to probably hit some of the questions again here in just a second, because I've been letting them go too long.
All right.
So one of the examples I like to give is, I'm trying to show off my steampunk lights here. One of the examples I like to give is if you're in a train, and let's say this is a train that can travel nearly the speed of the bullet, very, very close to the speed of the bullet. That's all fine and well, but let's just imagine for a moment that I have a magical time gun, and I can shoot the train with the time gun and slow down time inside of it. Now, if I close the shutters on the train, you can't look outside, and I shoot it with my magic time gun and slow time inside it, it's very important you understand that what you'll experience is nothing. You won't, it's no different than usual. You will not perceive that your time has been slowed. things will still fall according to you at the normal rate. You still be able to bounce a ball. You won't know anything happened so long as you keep the shutters closed. However, if you open up the shutters and look outside, what you will see is people running around really fast. And you'll be like, whoa, what's going on? Why are those people so fast? It's not that they're fast, it's that you're slow. And so your perception of them is what's wonky. They are not going fast. You are slow. And understanding that idea is critical to understanding all the problems with the twins paradox. But let's go a little bit further here. So I said that this is a train that travels nearly the speed of a bullet, and I've got a time gun. So let's first not mess with the time gun. Let's take that out of the equation for a moment, and let's have the train go past a person on the ground, and you've got the windows open and all, and allow them to fire a gun in the same direction as your train is traveling, and you look out the window. What are you going to see? Well, what you're going to see is a bullet slowly passing your window as it falls to the ground, because you're not traveling at the speed of a bullet, you're traveling just below the speed of the bullet. So it's going to slowly pass your window as it falls to the ground. And that's what you're going to perceive about it. Now, what you know, according to relativity, the constancy of light is, instead of that, the constancy of light says that whenever you're on the ground, somebody fires a laser, and if your train is stopped, you go look out the window and see the laser pass you at the speed of light, just like the bullet would pass you at the speed of a bullet. And then let's say you had a train that goes nearly the speed of light, and then what happened when you look out the window as you pass a guy on the ground who fires a laser in the same direction? Would you see, just like the bullet, the first wavefront of light creeping past you? No. According to relativity, it would be going past you at the speed of light. It's almost like no matter how fast you go, light goes faster by exactly the right amount. So it's a weird little relationship, right? And how could that be? How could that possibly occur? A lot of people will be like, oh, it's just time dilation. Let me explain this, though, in a more mechanically reasonable and sound manner. But that's going to require that I actually have something to drink. So if I've got the train that travels at the speed of the bullet, let's go back to that. I want to create the constancy of bullets, there where no matter how fast you go, bullets always travel the same speed according to you. And I'm going to do this with my magical time gun. So if you're out in a train that is traveling nearly the speed of a bullet, and you remember that whenever I shoot you with my time gun, things run around outside of your window really fast, right? Doesn't that mean that if you normally see the bullet just creeping past your window as it falls to the ground, that I could shoot you with a time gun and make your time slow just the right amount so that bullet passes by you at the speed of a bullet? Couldn't I do that? Even though you were already going nearly the speed of a bullet? And so it would make it seem like bullets there. Now I've created the constancy of bullets. However, I've created the constancy of the speed of bullets. However, there's a problem with this. And that is, what if somebody fires a bullet in the opposite direction as you pass? How fast would you measure that bullet? That bullet would be going almost 2 times the speed of a bullet. Oh, so I haven't done it yet. I have not created the constancy of the speed of bullets yet. So what if I don't allow you to measure the bullets in only one direction? I make you measure the average speed of bullets outside your window, no matter what direction they are. And if I have the same amount of bullets going up as are going back, but it just so turns out there is an exact calculation I can use to make it where you'll always see those bullets as going the speed of a bullet outside your window. If I slow your time just the right amount, make you only measure the average up and back, then you'll never see one bullet going nearly twice the speed of the bullet. You'll only get an average, and the average between them, I can always make it so that average is just exactly the speed of a bullet if I slow your time by a certain amount. That certain amount is the Lorentz Transform. That's what the Lorentz Transform does, is it creates this exact illusion I'm talking about. And that is, you can do it with the speed of you can create the Lorentz Transform for the speed of a bullet by messing with someone's time. And so that's the thing here I wanted to describe that probably should help you understand. Now, whenever I talk about the one-way speed of light, you understand why it is so crucial that you measure the one-way speed of light, not the two-way, because the average can always be screwed with by time. And I'm telling you that even in ether theory, your time is screwed with. That nature really is doing this illusion to everyone, just like it does with the Doppler effect, like I described earlier. Time really is screwing with your perception, and there really is also a shortening that occurs as well. It's that compensatory illusion really is occurring in reality, and that's what ether relativity tells you. And ether relativity tells you a completely different view of reality that fits completely, perfectly, mathematically within all of our current understanding, including things like why does time elapse faster in space? Well, because light is actually capable of traveling faster in space because of a different property of the ether there. And so there are things like the curvature of light around gravitational lensing, for instance. All of these things still work with an ether. It's just you have a different understanding of why they work. Matter of fact, you have an understanding of why they work, because before, with where we just believe the outside, we just believe the Lorentz transform is true. Forget all the mechanics that we were describing with math, because that's what math does. Math describes mechanics. It maps it. And if you just kill the map, which is what happened with Minkowski. Minkowski severed the map between mechanics and math and he was the first instance of shut up and calculate. And it was kind of an accident. And then he died before he was able to fix it. And then Einstein trying to fix it, nobody would listen to him. He kept saying, we have to discard constancy. There is a preferred frame. Space without ether is unthinkable. He went on and on and on about it. But because Minkowski died suddenly, nobody listened. They just didn't listen. And so, the thing is, another aspect of this, by the way, is that McCullough's ether, you remember me mentioning McCullough came before Maxwell, and he was part of this other type of ether that is the superior, that's not the jelly type of ether, it's the rotational elasticity type of ether. Well, McCullough influenced me, M-I-E, sorry. Maybe that's pronounced another way, but M-I-E, this is the name of one of the scientists of the day, who created a version of that's kind of like Minkowski's work, but it's a version based upon McCullough's ether. And that is what Hilbert used to help Einstein develop general relativity. General relativity was stuck in a slump for all of those years until Hilbert started working with Einstein and basically was teaching him about ether, because that's where his work was coming from, was from ether. Now, they didn't really think of it that way because they were it had already progressed to the point where people were focused more upon the math and less upon the model. But it was directly from, once again, there's two ways in which ether led directly to relativity. So does that make sense?
Yeah.
So, I do need to start answering some of these questions. Okay, so yeah, well, you can think about any other questions you want to put up there. I'm going to see if I can do some other questions to other people, but from the audience, because I'm not keeping up here. Let's see. Wait, so did I read that right? Yeah. Okay, so this is the next one. I don't think you can have a Doppler effect of light if light is not variable with respect to an observer. Thank you. Yes, I've pointed that out 15 years ago on the anti-relativity boards repeatedly. It's like, guys, if there's not, how can you have a Doppler effect? Here's the problem. When they believe that light is constant, they just give up the idea of mechanics entirely and just think magically. Because if light is constant, you can't have the Doppler effect. There's one way in which you can do it. You can think magically by adding another dimension and then say, well, light itself is cutting through dimensions. And it's just asinine. And I addressed that at other points, because it's built upon assumptions that are all basically, at the bottom, they're magical. So yeah, you can't really have the Doppler effect work if you don't have a variable speed of light. If you don't have a preferred frame, it doesn't work. But the problem is people don't understand how to deal with undefined variables, and that's what special relativity had, an undefined variable. In other words, there was the frame for all the speeds and all those things was left undefined. And when you leave it undefined, it's kind of like a divide by zero error. And actually, there's some calculator. There's some, like the relativity calculator right now, if you go to it, look at the JavaScript for it. If you try to put in, the speed of light as the actual speed for it to calculate, it gives a divide by zero error. And so it's because I don't want to get into that right this minute, but it's it's silly. Time dilation is probably a result of Doppler effect. Technically, maximum is already done in space. Light consistency is probably wrong. Yeah, so the anisotropic light speed constancy is true according to relativistic ether. So in other words, that there is an illusion that light will seem to be constant in all frames of reference is true in the modern ether that was available around the time of the Michelson Morley experiment, but just kind of things got confused. I guess it's just there's hey, they were all having to use snail mail at the time, the horse and buggies. Let's see. Only relativity has a paradox because it refused to have a stationary frame. Yes, exactly. The only reason you have a paradox in relativity is because of a lack of a preferred frame. With a preferred frame, there's no paradox. And every time that they say they've solved the paradox, they're just putting it off. And they've, under the covers, selected a universal frame and then pretended that they haven't. And it's like, oh my God, stop, please stop. You keep selecting a preferred frame as proof that you don't need a preferred frame. Oh, it looks like I lost Jerry. So yeah, that is a little ridiculous. And then everything is relativity, but when there is time dilation, there's time. The ether is always involved because the ether causes time dilation. It is the two twin plus the ether. Yeah, absolutely. There is you have to have the idea of the ether for the time dilation to have any mechanical reasoning. Otherwise, you're just buying into beliefs. And that's the thing. People don't use the word understanding properly. Understanding means that there's something under it. Belief is not understanding. You can believe in things. And a lot of times, whenever you say, okay, well, do we understand inertia? Yeah, inertia does this and that. And you calculate it this way, calculate it that way. No. Understand is in like something under it, something that makes it do that. And they don't get that a lot of times. And it's really weird that a lot of people really do not comprehend that understanding is not explanation of stuff around it. Because here's the thing. There was a time in which, even natural philosophers, people who were like the first progenitors of scientists, people who were investigating reality, trying to understand it. They had the idea of spontaneous generation. They thought, meat, when left out, produces worms. It just does. It spontaneously generates it. Now, they thought that they understood it because they could weigh it and say, like, okay, well, this period of time it takes, it produces this many worms per pound of meat left out. And then what's left over is this amount. And you can do all these calculations all around it. And knowing it is not understanding it. There's an under thing. There's something that leads to it. And when you just pick that level and try to do everything above it and everything beside it, that is not what is under it. And so they didn't understand spontaneous generation, even if they, could tell you just to the microgram, exactly how many, worms would be produced under what kind of heat conditions. And, they could go to just crazy extremes describing it happening without it ever addressing why it's happening. And that is not understanding. And people actually all very regularly get confused the difference between describing something and understanding something. And so the same thing is true with a lot of the things in science now, is that they don't know that they are simply describing and they're not giving an understanding, because the truth is we do have to put a stake in the ground. We do have to say, from here forward, because there is a problem of infinite regress. You can keep going, well, what was before that? What was before that? What's below that? What's below that? What's below that? And you can keep going and going and going, because like even what I'm talking about right now, when you talk about ether theory, well, this just gives us another layer down underneath why relativity is doing the relativity thing. It gives us a mechanical reasoning for why relativity does relativity. But there's another layer below that where you can start asking questions. Well, why this? Well, why this? Well, why that? You can keep going deeper. You can keep asking, what is infinity? Where do ether particles come from? What's the, if they're, let's say they're at the Planck scale, what's below the Planck scale? How does the Planck scale things contribute to the creation of your ether particles? And you can just do that infinitely. And, maybe that will be something left for the future, for future generations, but that's always, there is a necessity of putting a stake in the ground and moving forward. There's nothing wrong with that. And there is a necessity for orthodoxy. There's a necessity for these things, but they do eventually become a problem as well. In other words, your strengths eventually become your weaknesses. I mean, whenever you build a building, it is a good building at the time that you build it. And eventually you can keep adding to it and creating more stuff on top of it. And eventually the whole structure needs to be destroyed. The whole thing needs to be brought down to the ground and restarted all over again, because your needs have changed. The environment has changed. Everything has begun to change and has become obsolete over time. And so that's how knowledge systems are as well. So there's nothing wrong with what we've done so far. We just have to be able to still have revolution along with the orthodoxy. We need the orthodoxy. We need the regular science. This is Thomas Kuhn. I'm paraphrasing Thomas Kuhn. You need the normal science effort to find all the stuff that may be wrong with your current stake in the ground, your current thing that you're going with to try to progress. And that's how you lead to progress. You make some assumptions. We have to make assumptions. It's a necessity. But you still have to have room for revolution as well. And that is the point we're at. We're at the point of revolution, and people do not want to let go of the orthodoxy. And that's where we've got a problem. I don't know where, I'm gonna have to send him a message, see if I lost him. Spontaneous, yes, it's wave particle duality. It just is. They don't tell you why it is, how it is, what it's doing, where it just is. Just believe it, shut up and calculate. Shh, we don't talk about that. Well, I talk about that. Ether theory provides for that which is underneath wave particle duality. It gives you a mechanical reasoning. It gives you a way that it works. And why is this important? Because of the extension of our theory. The extension of our theory, what we're talking about is save the world stuff here. I mean, it really is. If we can revolutionize physics, if we can just stop for a moment and say, hey, maybe the direction we've been going in research needs to open up a little bit. Maybe we need to rethink the direction we're going. How do you know what direction to go to find the unknown, to find the next thing, to revolutionize your knowledge system? How do you know what direction to go? That's what theory is for. And you have to take the gestalt. You have to take all of the things that you've learned and compare them and put them together in different ways to figure out what direction you should be testing to find the future of your knowledge system. And the direction is determined by your theory, and our theory right now is obviously wrong. And if we can just update the theory, then we can change our direction of research. If we change our direction of research, then we may be able to revolutionize energy. And energy lies underneath the whole climate change issue, lies underneath all of the war and inequality. It lies at the heart of all human suffering, truthfully. And so, what I'm hoping to get people to do is to go along with me on this ride and say, hey, we need to get people to look at this alternative viewpoint so that we can have the possibility of testing, that we can have the possibility of funding for a different direction in research. I'm not saying, hey, I'm absolutely right and all you guys are wrong. I'm saying this is an alternative direction for research that we need to look at because it has validity and it gives a perspective that is different and will allow us to test certain things that have not been tested, that have not been proven, and it gives us a way to understand things in a way that we've never understood them before, and they make perfect sense, and it is where we were going before, and we just lost track of it. That's how science got where it is right now, is because of the ether. The ether is what got us here, and what got us topology, knot theory. It's what got us all of these different mathematics that we use. We just cut there is a map and there's territory. And we just cut the connection between the map and the territory, started believing, well, the territory doesn't even exist. All we gotta do is move around the objects on the map, and that's how we'll figure things out. We'll figure out everything from that. It's like, no, math represents something. It represents something, and you can't just disconnect the representative language from what it represents. And that's what we did, is we disconnected them accidentally, but we did it. Black hole is black. Why black hole would be black is just because there's because it's a vacuum of ether. When in terms of ether, it's an actual vacuum. There's no substance for it to travel through. There's no travel. So it's just like there's no air in space, so no waves can travel through space. So basically, space is a black hole to sound waves. Well, the black hole would be, no ether for it to travel through, or at least the ether is so disturbed that it has to wrap all the way, that the light has to wrap all the way around. It can't go straight through, or something of that nature. So yeah, the idea of a black hole is basically a gigantic cavitation, a gigantic cavity in the ether. And basically, from the idea of ether theory, let me check with him real quick, but from the perspective of ether theory, matter is basically the edge of the universe, as are black holes. If black holes truly do exist, there's still there's definitely some phenomenon that is black hole like, that has definitely been recorded as occurring. There's something at the center of the galaxy is making things, wrap around really quick, and there's definitely some black hole like effects. But if it's whether it's exactly the way that we describe it or not, that's up for debate. But the reason why it would be black, why we wouldn't be able to see through it, is because it's either disturbing the ether so much that light waves go just right around it, or because it's specifically a cavity. And I believe that at the bottom level, it's almost certain that particles, that make up atoms, are cavitations in the ether. In other words, there's literally places where the ether is ripped apart and there's no ether there. And so that is actually what physical matter, that is the difference between physical matter and non-physical things, is that there are cavitations created within the ether because the ether is so disturbed at the level of matter that it is crossing a threshold, just like that threshold of a tornado. When a tornado travels so fast, is spinning so fast, it changes the properties of the medium, the air, such that there is this transition point where you can suddenly start seeing the border. It's not a real border, but it's a border in a certain way. It's both real and not real, and that's what's occurring with matter as well. Welcome back.
Oh, thank you. The computer just shut down.
Oh.
Sorry about that. The computer shut down on me.
Oh man. Hey babe, can you turn the air conditioning off back on? I think you sabotaged me. I'm over here sweating to death underneath these lights. Thank you. So yeah, you had some more questions. Oh wait, I think I still had one more comment here I needed to cover. Let's see. Why would everything rotate around nothing? No, it's not rotating around nothing. It's the rotation is creating nothing. So you're getting the cause and the effect mixed up. Matter is the effect. The rotation is the cause. In other words, the ether is the cause of matter, not the other way around. Gravity is an aspect of the changes to the ether around matter, but matter itself is an epiphenomenon of behavior of ether. In other words, behavior, giant. Okay, what the galaxy is giant areas. Just like if you were to see two laminar flows of water or of some fluid, as they go past each other, what you have between them is generally called turbulence, which means there are these tiny little vortices that are allowing these large sections to move past each other. And when you were a kid, maybe you did your hands together like this, and you were a dirty little kid, and you had little funky things left over in your hands. Well, it's kind of like the creation of galaxies and all matter in general, is that these giant bodies of ether moving past each other are spinning them up into what we think of as matter. And so the creation of matter is constantly a process that is occurring. It is a constantly maintained process where matter is emergent from the forces of ether and the motion of the ether and the basically the interaction of different sections of ether are what create matter. So in other words, ether is the real thing. We are simply the borderlines of the universe. In other words, matter is the borderline, is the foam at the edge of the sea. All right, man. You let me remove this from here. And so, yeah, if you had some more questions, stuff, let's hit them.
Well, I was sort of quickly reviewing everything that I had over here disappeared. So now I'm having trouble collecting my thoughts. Actually, I mean, I think I basically asked the main questions of, just what I wanted to see what you thought about. I mean, there's a lot more, but it mostly derives, like they're all related to what things that mentioned. So they're just asking about.
And some of them, of course, I try to hit root things, so it's going to cut off certain questions by the very nature of changing the nature of the understanding of what's below it. So yeah, I understand. I may have invalidated some of the questions that you had because they don't fit with what I've now told you.
It became irrelevant, or the point was already expressed.
Right.
Anyway, I guess I'll sign out for now.
Okay. Yeah, and maybe when you chew on this some, you can come back with some more questions. I really appreciated your ability to ask questions. That's that has been.
Well, thanks very much for having me.
Something I need.
All right. Well, I very much enjoyed the conversation. Thanks for having me, and I'll talk to you soon.
All right, man. Good talking to you. I'll see you online out there.
All right.
Take care, Jerry.
Thanks, man.
So let's see if we've got any more questions, comments, etc. here in the chat. Doesn't look like there is. So so hopefully. Well, this is kind of a new thing for me. I just, Jerry's a nice guy and had lots of good questions, and was a skeptic about the ether, and so that's kind of what I'd like is people who are skeptical but ask questions and are open minded, and that's if we can get more people like that, asking the right questions, and basically, there'll be more people who have the large picture and how it all works together in their head. Because the truth of the matter is, I can't have this just be with me, the full understanding of all of it. I'm trying to put it all in the book, and hopefully I'll be able to successfully put all of it in the book. But I've already put so much of it out in, the questions on Quora. There's lots of questions on Quora. There's a couple of different things I put on. Let's see, relativitydemystified.quora.com was like one of the little things I added to my Quora profile. Wow, yeah, I'm starting to lose my voice here. And but if there's any of you out there that would like to ask questions and bring you on, and let's just talk about it, because that's going through the questions and having a conversation between people really is useful. It's useful to me in my process. Why I invited him on here. He was saying like, yeah, we could talk about it other times. Like, no, I want it recorded so that it's useful for me in working forward on my book, because I've spent over a decade freely sharing a lot of this information and teaching individuals and going from individual to individual to make sure that the info gets out, so that more people understand it, more people understand the problems with current physics, more people understand that I'm not arguing against Einstein, I'm arguing for Einstein, and you guys are arguing against Einstein when you say that you're arguing for Einstein, because you didn't read the history. You don't know that Einstein didn't say it that way. He didn't believe it that way. And it's, that's by itself is such a mind-boggling thing. It's just, it's really weird as a sociological thing that's happened where we've forgotten history. And so, just getting that out there, where there is this alternative, viewpoint that's like, hey guys, we all forgot history. It's right there. You can look it up. It's not hard to find. You can go and look and read the things that he said, but there's just a lot to sift through. And so not a lot of people can do that sifting. And that's what I've been doing. Sifting, re-educating, and anybody who can come at me with some more questions. That's why I like Quora. Is going to help make it where other people who don't have my perspective can say, hey, well, what about this? Or what about that? Because my perspective is one that has developed over many years and just tons and tons of study of the history of relativity and the history of physics. And eventually you kind of have a level of normality to your viewpoints that make it where you could speak in terms that are very concise, but they're too concise. You're referring to things that people don't know. In other words, I accidentally refer to very complex subjects that people don't know, and sometimes it feels so mundane and everyday to me after 20 years that it's that basically I'm accidentally doing that whole thing where people use like acronyms and they obfuscate things. So sometimes I need people who don't know that much about it, but are also skeptical, and they're like, "Hey, what about this? What about this? What about this?" I need those questions. I need those. So that's why it was useful for me to have Jerry on. I appreciate him coming on. And if there's anybody out there, I did have sort of a conversations with physicists thing I was going to start doing. I do have that one video with the good friend of mine who's a physicist, and I planned on doing more, but this was I thought it's like this guy's got a lot of questions. He's been really interested in it, so let me invite him on, and we'll just talk about it. We'll have a conversation that other people can participate in. If you guys have lots of questions, anybody out there who's watched this or is watching it right now, please do post it, and maybe we'll just come on and have a conversation. Hey, say you want to be like, "Hey, dude, you don't know what you're talking about. You're crazy." Sure, I'll have you on. I don't care. That's great. I would love having somebody who's just all about like let's have you on. Let's talk. That'd be fun. So not just the people who are agreeing with me. Let's hear some voices that are dissenting with mine. I mean, even though the whole world is filled up with voices that are dissenting to mine, that is, let me be very clear here. My view is extremely outside of the consensus. I'm very proud of that. I know my viewpoint is well outside of consensus, and I don't care, because what I'm saying is consensus goes wrong. That's the nature of consensus. It has to have orthodoxy, and that orthodoxy has to fail over time. That's just reality. So, but please do come on or at least contact me, and we'll see if we can set something up. I'm trying my best to focus on the book, to focus on getting it done, and putting all those things together. And so I might not have the time, but if you have like a good list of questions, I might be able to, put some time together and let's just chat. So yeah, thanks to Jerry for the questions. Let's see. Looks like we've got some other questions here in the chat. Oops, there we go. Do you think quantum mechanics will survive the next 10 years? Because it seems to be struggling. Here's the thing. Yes, I think it will survive the next 10 years because there's a lot of work that has to be done. Here's a good analogy. Windows is failing. I'm just going to say that right now. Windows is, as an operating system, gets worse every time it comes out. I haven't upgraded mine. Maybe they did some rewriting, but the problem with a piece of software is that it's a way of doing things, that, and then once you have a lot of people using that way of doing things to accomplish meaningful tasks, they need it in their everyday work to do other stuff because they're doing other things. So it's a system that helps them do their other things. And our current orthodoxy is a system that helps people do other things. And it does it. And so certain current quantum physics does things. It accomplishes valuable tasks. And just like if I wanted to rewrite Windows, say, for instance, Bill Gates says, the whole Microsoft, it's yours, do what you want. I would not be like, all right, that's it. Today we're rewriting Windows from scratch and putting it out. That would actually be kind of a bad idea. You have to roll it out over time because there's all these people who are relying on all these different suites of products that are working specifically for this version of Windows. Yes, Windows is this big ball of crap that is developed and developed and developed to the point at which it needs revolution. It needs to be rewritten from scratch. It does need that. But do you immediately do it? What you're talking about is such a monumental effort to try to get everybody over to a new operating system, all the different software suites that are written to work with Windows, all the manufacturers, all the product assembly lines, it's what you're talking about is like Manhattan Project level. It could only be a public works project to rewrite Windows at this point. With as many billions as Microsoft has, I don't think they could do it because of the level of funding that would be required to get everybody over to this new system. So it's going to be the same thing with quantum computing. Getting people over to systems is going to have to happen over time. It's going to have to be rolled out in phases. And so, yes, quantum physics is definitely going to survive the next 10 years, probably the next 20 years, even if today, every physicist out there goes, hey, dude, you're right, and all these other people are right. We're switching over to ether physics today. They all do it. It still can't be done today. It can't be done today because there are too many people still using the structures and the methodologies that are workable. They function within the thing that they're supposed to function, and they do something. And yeah, I hate Windows. I think Windows is a big pile of crap, but I'm still using it right now. And so the same thing will be true of even if this is the right way of going, but at the same time, we may be able to still have research that goes forward alongside. So in other words, just like quantum computing, let's say they actually get it right. It has to be able to be applied to some of these other systems. And right now, it only has certain applications that it's even useful for. But those are very important applications. And so it's more specialized. So the thing is, what I'm hoping for will actually be a specialized offshoot of physics that will eventually come back in and slowly change together. In other words, mainstream physics orthodoxy will slowly change with this offshoot of research that is going into the future, because they still have to use all of their well-established and useful things like, people are still using electron holes today. They're still calculating based on electron holes. They don't care that it's bullshit. It's still useful to them. And so we need to not care that it's bullshit if it's still useful for particular things. It's still useful for particular things. That's just all there is to it. So the usefulness will still be there in quantum mechanics for some time. But we're headed down a path with climate change and use of fossil fuels and our problems with trying to make not alternative energy, but you know what I mean. In other words, these sources of energy that are at least more carbon neutral, at the very, all of those sorts of things. There are even some advancements that will be made there with the current system. But if we really want to make leaps, huge leaps in the tiny time frame that we have, we need to be able to completely revolutionize and be looking at radically different perspectives. And we need to be researching radically different perspectives. And so we need the people who are still using the old system, and we need people using the new system. And so yeah, I don't believe that current quantum mechanics will just go away. I don't think it should just go away. I think that what we need instead is an opportunity for funding in an alternative research area that could lead to massive advancements very quickly in the time frame we need to save ourselves from going off the cliff. You can look me up as Shiva Meucci. That's Meucci. And let's see, relativitydemystified.quora.com is like a little, I don't know, they had for a period of time, you can create your own like kind of page on Quora. That you can't do that anymore, but I guess I got in under the line there. Just like on my YouTube channel, I've got steampunk physics at YouTube or something like that. I don't know. It's like .youtube.com, or maybe it's YouTube/steampunk physics. I don't know, but it's one of those things where I kind of got grandfathered in. But yeah, it's Shiva Meucci. You can also find my papers published in Cosmos and History. It's a philosophy journal, because basically that's what we're talking about here. Whenever you're talking about a change in that doesn't, if you're not talking about altering the mathematics and keeping most of the mathematics the same, then what you're talking about is it's technically called metaphysics. And I hate that the term metaphysics is also a term used for things that are not metaphysics, but just magic, because I'm very, very, very much against magic. And I'm saying that there's magic in the current physics. And so when you're talking about the way that we come to our understanding of things, the way that we examine our experiments, and the way that we deal with our cognitive biases, all those sorts of things, those are technically philosophy. And so that is so that's where my papers are in. And Cosmos and History is technically a philosophy journal. It is a philosophy of science journal. And you'll find there's some other great authors there that I've collaborated to some extent with as well. So I actually haven't done a paper with any of them yet, which I plan on doing soon. But so yeah, Shiva Miyuchi, Shiva, and my last name is Meucci, and you can find my papers. I think they probably show up at. I think that there's a group of them that shows up at the Phil People. Yeah, that's right. There's a site called Phil People that that has my most recent draft on Minkowski spacetime, and I got that's actually my next goal, is to finish that paper. I do this thing where I put out a draft of a paper, and it takes me a year to get back to it to finish it off. I do the important part first, and then come back and finish it out. And so that's where I'm at with this draft that's been sitting there for about a year. But it's really good as it is as a draft, and I think you might like it if you check it out. So. Yeah, if that's it, then thanks a lot for joining me, guys, and thanks for the questions. I really appreciate it. And again, please start bringing in more questions. That's question everything. And if you, that's one of the things that I have a hard time with, is a lot of people who call themselves skeptics are actually just orthodoxy people. In other words, they don't understand that questioning means you question your own beliefs. What are your beliefs? Question those. Then, and especially questioning, what are the beliefs of your preferred group? Because if you just believe all the things that your preferred group does, you cannot call yourself a skeptic when you start questioning those people who are not part of your preferred group. That is not skepticism. That is basically religiosity. And I say that with, I have respect for religion, of course, but there are aspects of religious behavior, and that's why I actually, my respect is more for spirituality and things of that nature, but not as much for organized religion, because the organization leads to these orthodoxy behaviors that that are called zealotry and things of that nature. So there are issues that I have with people behaving that way in science, and you don't need to actually believe in anything spiritual to behave in a somewhat religious way. And that's what I want to get rid of, is these sorts of behaviors. And so if we could just start asking questions again, that's really what I want. So yeah, it was really good talking to you guys. Yeah. Herd mentality is good. You're exactly right. Do I know you? You sound like you've got a lot of the same opinions as me. There are good things to being part of the group, being finding some unity with the group, very important. But also sometimes unity with the group can lead to a stampede. So there is that as well. Goodbye. Good night. Yep, there are many zealots, and zealotry has nothing to do with spirituality. It just has to do with the mental behavior about your own beliefs. So, yep. Great talking to you guys. Good night, everyone. Thanks for coming.